Hey guys, welcome to the session by Intellipaat. Now you guys would have heard of Google's self-driving car, a car which drives by itself. Now that is truly amazing, isn't it? And this revolutionary technology is possible because of artificial intelligence. And to implement artificial intelligence, you would need some tools. So this is where deep learning frameworks come in. And in today's session, we'll work with the Tensorflow deep learning framework. Now before we start with the class, do subscribe to our channel so that you don't miss out on our upcoming videos. Also, if you're interested in doing an end-to-end certification course in artificial intelligence, then Intellipaat provides us the right course to gain all of the requisite skills. So let's have a quick glance at the agenda. We'll start off by understanding the terms artificial intelligence, machine learning, and deep learning. And then we'll comprehensively learn about artificial intelligence. After that, we'll look at some deep learning frameworks and have an introduction to TensorFlow. Going ahead, we'll learn about neural networks. After that, we'll be implementing a demo on the MNIST dataset using TensorFlow. So guys, without much delay, let's start off with the class. So I'll start off by asking a very simple question. So tell me, what is it that makes humans intelligent? Well, we as humans can think, learn, and make decisions. And that is what makes us intelligent. Now imagine if machines can show human-like intelligence. A machine which can think and make decisions like humans. That is truly amazing, isn't it? So, artificial intelligence is basically that field of computer science which emphasizes on the creation of intelligent machines which can work and react like humans. So now that we know what artificial intelligence is, let's see where do machine learning and deep learning fit in. So you can consider artificial intelligence to be the broader umbrella and machine learning and deep learning to be a subset of it. Or you can also say that machine learning and deep learning are a means to achieve artificial intelligence. Now, let's see what machine learning is. So, machine learning is basically the subset of artificial intelligence where we teach a machine how to make decisions with the help of input data. So, we'll understand machine learning with this little example. So, what do you see over here? What is this exactly? Well, it's a bird. And what about this? This again is a bird. And this? Well, this too is a bird. Now, how do you know all of these are birds? Well, as a kid, you might have come across a picture of a bird and you would have been told by your kindergarten teacher or your parents that this is a bird. And your brain learned that anything which looks like that is a bird. And that is how our brain functions. But what about a machine? Now, if I take in this image of the bird and feed it to a machine, will it be able to identify it as a bird? So this is where machine learning comes in. So what I'll do is, I'll take all of these images of the birds and keep on feeding them to the machine until it learns all the features associated with it. And once it learns all the features associated with it, I'll give it new data to determine how well it has learned. Or in other words, first I'll feed in training data to the machine so that it can extract or learn all the features associated with the training data. And once the learning is done, I'll give it new data or the test data to determine how well the learning is done. And this is the underlying concept of machine learning. Now let's head on to deep learning. So deep learning is the subset of machine learning where we develop intelligent algorithms which mimic human brain. So now the question which arises over here is, how do we mimic human brain? Well, to answer that, let me ask another question. So what is a brain composed of? Well, our brain is primarily composed of neurons, isn't it? And these neurons send and receive electrochemical signals. So we have a neuron over here and the electrochemical signals are received through the dendrite. The processing of these signals is done in the cell body and the output of these input signals is sent to other neurons through the axon. And if our task is to mimic human brain, all we have to do is create artificial neurons. And these artificial neurons work the same way as biological neurons. So to implement deep learning, we'd have to create artificial neural networks. And these artificial neural networks comprise of an input layer, a hidden layer, and an output layer. So all of the inputs are received through the input layer and the processing is done in the hidden layer and the final output is received through the output layer. And to sum it up, artificial intelligence is the broader umbrella, machine learning is the subset of artificial intelligence, and deep learning is the subset of machine learning. And machine learning and deep learning are basically methods to achieve artificial intelligence.
So let's understand why should we study artificial intelligence. So why AI? Well, AI is actually everywhere. It's omnipresent like God. And AI's applications are present in every single industry, from banking and finance to medical science and also in aerospace. Now, it is actually a known fact that many banks have numerous activities on a day-to-day basis which need to be done accurately. And most of these activities take up a lot of time and efforts from the employees, and at times there is also a chance of a human error in these activities, so to speak. So, some of the works that banks and financial institutions handle are investing money in stocks, financial operations, managing various properties, and so on. And with the use of AI system in this process, the institutions are able to achieve efficient results in a quick turnaround time.
Right, guys, just a quick info. If you're interested in doing an end-to-end certification course in artificial intelligence, then Intellipaat provides us the right course for you to master all of the concepts with respect to this field. And you can check out the course details in the description below. So let's continue with the class.
So, the strategic implementation of artificial intelligence in the bank helps them to focus on every customer and provide them quick resolution. And similarly, in medical science field as well, it has wide applications. So, AI has completely changed the way medical science was perceived just a few years ago. So there are numerous areas in medical science where AI is used to achieve incredible value. So with the help of AI, the medical science was able to create a virtual personal healthcare assistant. So these are used for research and analysis purpose. There are also many efficient healthcare bots introduced in the medical field to provide constant health support to patients, and it is also used in the aerospace industry. So in aerospace, there are a lot of features from booking the tickets to the takeoff and operation of the flights that AI takes care of. AI applications make air transport efficient, fast, safe, and also provides a comfortable journey to the passengers. And it has also changed the face of gaming. So these days we are able to play TV and computer games on the whole new level, all thanks to artificial intelligence application. So these are just some of the applications where artificial intelligence is used, and all in all it is used to reinvent the world. So scientists are riding on the back of AI when machine intelligence will surpass the human intelligence. Scientists believe that once the AI system starts working in its full capacity, it will reinvent the world that we know today. So think of the world where all the menial tasks such as garbage disposal, construction, digging, and so on will be taken care of by AI applications. So it'll all be a time when the hierarchical order dictates the limits of a human. It'll be the world where no one will be looked down upon and every human will be considered equal. So this way, humans can then focus their strengths on higher levels of work to accomplish a lot more, and always taking technology to new heights. So now that we've understood the importance of artificial intelligence, let's learn more about AI. So AI is basically a field of computer science which emphasizes on the creation of intelligent machines which can work and react like humans. So I am reiterating it. So AI is that field of computer science where we create machines which can work and react like humans. So let's keep this definition at the back of our head. Using this definition, let's actually look at some applications of AI which are currently existing in today's world. So we have simple chatbots like OK Google and Siri, which help us in assisting whatever we want. So let's say I want to know the current time. All I need to do is ask Siri, Siri, tell me what is the current time. Similarly, if I want to know the distance between India and Malaysia, I'll ask Siri, tell me what is the distance between India and Malaysia. Again, let's say I'm just sad and I want to listen to a simple joke. I'll ask Siri, tell me a simple joke. Alright, so these are some of the applications of artificial intelligence. And then we have Sophia. So Sophia is the first humanoid robot. So she is the first humanoid robot who can actually speak to us like natural humans. So Sophia can show some wide range of emotions exhibited by humans, but she is actually a robot. Another application of artificial intelligence is the self-driving car. So you have self-driving cars by Google and Tesla, which actually drive by themselves. So they do not need any external driver to drive, right? So these cars work by themselves. So similar to self-driving cars, we also have self-flying drones, which do not need any human intervention and they can navigate by themselves.
Right, guys, just a quick info. If you're interested in doing an end-to-end certification course in artificial intelligence, then Intellipaat provides us the right course for you to master all of the concepts with respect to this field. And you can check out the course details in the description below. So let's continue with the class.
So now let's actually get a bit deeper and understand what is intelligence. So intelligence can be defined as one's capacity for understanding, one's capacity for self-awareness, one's capacity for learning, and one's capacity for problem solving. That is, how well is something or someone able to understand? How well is someone able to learn new things? And how well is someone able to solve problems by themselves? So, now that we know what is intelligence, let's understand what is artificial intelligence. So, when you apply the same intelligence to machines, this is known as artificial intelligence. Now, just imagine there's a machine which can understand things which are normally understood by human. There is a machine which is self-aware, and there is a machine which can solve problems by itself. Now that's just amazing, isn't it? Right. So this is the artificial intelligence which I'm talking about. So now that we also know what is intelligence, I'll ask another question. So tell me, what is it that makes humans intelligent? Well, we as humans can reason, we as humans can learn, we can perceive, we can solve problems, and we also have linguistic intelligence. That is, we can figure out what is someone else saying, and we can also understand the grammatical intricacies of different languages. So, again, my question would be, what if a machine could exhibit all of these factors normally shown by a human? Again, that's just amazing, isn't it? So this is what is known as artificial intelligence. So a machine which can show traits normally shown by a human, that is known as artificial intelligence. Alright, so now that we're clear with artificial intelligence, let's segregate AI, ML and DL. So normally most people get confused between artificial intelligence, machine learning and deep learning. So this is where I'm going to help you out in understanding the difference between these three. So we have AI at the top, and you can consider machine learning and deep learning to be subsets of AI. So again, machine learning and deep learning are just ways to achieve artificial intelligence. So I'll restate it again. Machine learning and deep learning are just ways to achieve artificial intelligence. Now, machine learning is that part of artificial intelligence which aims to teach the computers the ability to do tasks with data without any explicit programming, right? So we don't need to do any explicit programming, and the algorithms do tasks by themselves. And in ML, we mostly use numerical and statistical approaches to achieve artificial intelligence. And then we have deep learning, which is actually a subset of machine learning. So first we have AI, and then we have ML, and then we have DL. So deep learning comes in where machine learning fails. And we apply deep learning through something known as artificial neural networks, about which we'll obviously learn later. Right. So now let's understand artificial intelligence in a bigger set. So as I've already told you, artificial intelligence is the superset under which comes machine learning, under which comes deep learning. And then machine learning and deep learning are basically ways to achieve artificial intelligence. Now these are the different areas of research of artificial intelligence. So you have ML. Again, a part of ML is deep learning. Then we have natural language processing. So over here we basically understand what is spoken or written by a human. And then we have speech, where we either translate the speech to text or we translate the text to speech. The next subfield is robotics, and then we have autonomous vehicles under robotics. So Google self-driving car is an example of this over here.
Right, guys, just a quick info. If you're interested in doing an end-to-end certification course in artificial intelligence, then Intellipaat provides us the right course for you to master all of the concepts with respect to this field. And you can check out the course details in the description below. So let's continue with the class.
So now that we've also understood the difference between artificial intelligence, machine learning, and deep learning, let's see different examples of machine learning around us. So most of you would have shopped on Amazon. Now, when you go into Amazon, you see that there are some products recommended to you. Now, how do you think that would happen? So this is something known as recommendation engine. And recommendation engine is nothing but a component of machine learning. So let's say you and your friend buy similar products. So your friend buys 5 products and you buy 3 products. Now, out of those, whatever 3 products you buy are same as what your friend buys. So let's say the common products are an iPhone, a back cover for the iPhone, and a Bluetooth headset. Now let's say the other 2 products bought by your friend would be a MacBook and a mouse. Now since there are 3 products which are same between you two, this is why the products which your friend has also bought, those are the products which will be recommended to you. So on the basis of the commonality between you and your friend, you will be recommended a MacBook and a mouse as well. So this is nothing but a concept of machine learning. And then we have Amazon Alexa. So Amazon Alexa is a really good example of speech recognition. You know, when you say Alexa, turn on the lights, it'll turn on the lights. When you say Alexa, book a ride for me, it'll do exactly that. When you say Alexa, order a cheese pizza, and that is exactly what Amazon Alexa will do. Now Alexa is just a machine, right? But when you say do something, order a pizza, book a cab for me, turn on the lights, how is the machine able to understand all of this? So the idea behind this is speech recognition, and that is again a component of machine learning. And then we have Netflix's movie recommendation. So let's say you watch 2 TV series. First TV series is Friends and the next TV series is Big Bang Theory. And since you watch these 2 TV series which belong to the genre comedy, that is why maybe you will be recommended How I Met Your Mother, or you can be recommended Silicon Valley or some other TV series belonging to the comedy genre. So this again is machine learning. And then we also have Google traffic prediction. Let's just say you're traveling in your car and there is huge traffic there. You desperately want to get out of the traffic. So you turn on Google Maps and Google Maps tells you the best direction from where the traffic would be the least. Now, how does Google Maps do this? This again is machine learning. So now that we've looked at different real-world applications of machine learning, let's actually understand what exactly is machine learning. So, as I've already told you, machine learning is a subset of artificial intelligence which gives the machine ability to learn without being explicitly programmed. So over here, data is the key, or in other words, you basically teach a machine how to learn without any explicit programming, and the machine learns with the help of data. So now that we know what exactly is machine learning, let's also understand how does machine learning work. So as I've already told you, machine learning depends totally on data. So first, we take in a data set and divide it into 2 parts. So the first part would be the training set and the second part would be the testing set. And we will train the model on top of the training set. So now, once we train the model, we will give it new data and check for its accuracy on top of that new data. And if the accuracy of that new data comes out to be good enough, then we will go ahead and use that machine learning model. On the other hand, the model which you built, if the accuracy of that model is not good enough, then we'll go ahead and fine tune that model till we get the desired accuracy. This is the basic premise behind machine learning. Now let's look at the subcategories of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, you can consider that the learning is guided by a teacher. So we have a data set which actually acts as a teacher, and its role is to train the model or the machine. So once the model gets trained, it can start making a prediction or decision when new data is given to it. So let's take this example. So over here, we are training this machine by giving it samples of data. So over here, the data is nothing but different images of apple, and along with each image of apple, we are also giving it the label of the image, right? So this image goes with its label, which is apple. Again, this image goes with its label, which is apple. Again, the same with these two, right? So we are teaching this machine that whenever it sees an image something like this, it is nothing but an apple. And after time, when we give it a new data, from whatever learning it has done, it will predict whether it's an apple or not. So on the basis of its learning, this machine predicts that there is a good possibility. There is actually 97% possibility that the image which has been fed to the machine is nothing but an apple. So a use case of supervised learning could be spam classifier. So spam classifier basically means that whether the email which we get it's a spam or not, and that is done on the basis of different textual parameters. So let's say a genuine email wouldn't contain too many exclamation marks, it wouldn't contain a catchy headline and so on. But on the other hand, if it's a spam email, maybe it will contain a lot of exclamation marks with maybe a lot of numbers, and it'll have statements like, hey, congrats, you've won a lottery, or hey, could you help me out? So this spam classification is basically an example of supervised learning. Then we have unsupervised learning. So in unsupervised learning, the model learns through observation and finds structures in the data. So once the model is given a data set, it automatically finds patterns and relationships in the data set by creating clusters in it. So what it cannot do is add labels to the cluster. Like it cannot say this is a group of apples or mangoes, but it will separate all the apples from mangoes. So over here we have this set of images. Now this unsupervised learning model which is applied on this, it will segregate these fruits on the basis of similar characteristics. So over here we have segregated these four into one cluster, these three into second cluster, and these three into the third cluster. Now even though the unsupervised learning does not have any labels, it has still segregated these three into three clusters, right? So the machine over here does not know that these are apples or these are oranges or these are bananas. Yet it has segregated these three on the basis of similarity of characteristics. So it found out that these four objects are similar to each other, and there is quite a bit of variability when it comes to these four objects and these three objects. Similarly, this machine was able to figure out that these three objects, they are quite similar to each other. But when compared with these three objects, they are very dissimilar. So this is the underlying concept of unsupervised learning. And a good example of unsupervised learning would be again Netflix movie recommendation. So over here, the movies are segregated on the basis of different genres. So over here, TV series like Friends, How I Met Your Mother, and Silicon Valley are clustered into one group because those come into the same category. Similarly, movies such as Secret Superstar and Dangal could come under the same category because they have the same lead actors. So over here, we are segregating the movies on the basis of similar characteristics, even though there are no labels in it. And it's finally time for the third machine learning type, which is reinforcement learning.
Right, guys, just a quick info. If you're interested in doing an end-to-end certification course in artificial intelligence, then Intellipaat provides us the right course for you to master all of the concepts with respect to this field. And you can check out the course details in the description below. So let's continue with the class.
So over here, there is an agent and there is an environment, and the agent interacts with the environment and finds out what is the best outcome for it. So it basically follows the concept of hit and trial method. The agent is rewarded or penalized with a point for a correct or a wrong answer. And on the basis of positive reward points gained, the model trains itself. So let's take this example. So over here, this self-driving car would be our agent and the road is the environment. And this car is interacting with this environment. So it will observe the environment and it has two choices over here. So either to go straight or turn right. Now, let's say this agent or this self-driving car decides to go straight. Then what happens is it goes and bangs straight into this barricade. So then it realizes that the action taken by it was not in its best interest and that is why it is penalized. So since it is penalized, it realizes that the action taken by it was wrong and that is why from the next time onwards it will do the opposite action. So instead of going straight, it will take the right turn. And when it takes the right turn, it realizes that the road is correct and the agent is rewarded. So this is how reinforcement learning basically works. So the agent interacts with the environment, it takes an action, and if the action turns out to be incorrect, it is penalized. And if the action turns out to be correct, it is rewarded. So this cycle goes on and on till it completely learns its environment properly. And the best use case of reinforcement learning is again self-driving car. So companies such as Tesla and Google are working on these self-driving cars. So just to sum it off, these are the three different types of machine learning algorithms. So we have supervised, unsupervised and reinforcement machine learning. So under supervised we have regression and classification, and in unsupervised we have clustering techniques, association analysis and hidden macro model. And then the third is obviously reinforcement learning, which works on trial and error method. And if you want to do some really cool machine learning projects, you can check the sites out. Now let's look at some limitations of machine learning. So when it comes to machine learning algorithms, they would require massive stores of training data. So again, as I've told you, machine learning is totally based on the data which it has. So if you have more amount of data, only then it will be able to give correct accuracy. So let's say you take in very small amount of data and there's a good possibility that the results which you're getting are very biased or very incorrect. And also, error diagnosis is quite difficult when it comes to machine learning because again the amount of data is very huge and wherever there's a mistake, you'd have to go through the entire algorithm which you've written and then find out that particular mistake by yourself, which is very difficult. And also when it comes to machine learning algorithms, they're not really that creative. So these ML algorithms are built only for one specific purpose. So let's say I'll build a machine learning model which will predict whether it will rain or not today. Now, if I want to use the same model to predict the stock prices, that will not work, right? So basically one model is built only for one particular task. So this is the lack of creativity that I'm talking about when it comes to machine learning. And also there are a lot of time constraints as the model has to learn through a lot of historical data. So that was everything about machine learning. Now let's start off with deep learning. So deep learning is a subset of machine learning where it learns through data representations as opposed to task specific algorithms. So we saw that the drawback in machine learning models was that the models are specific to only one particular task. But this is not the case with deep learning models, as these deep learning models are based on the data representations, and these deep learning models are mostly built with something known as deep neural networks. So this is how a deep neural network looks like. So these deep neural networks completely learn the data which is fed to it. So this is the data. So let's say if this image of woman is fed as the data to the deep learning model, then it will completely extract all the features of this data by itself. Again, the difference between ML and deep learning over here is that the feature extraction in machine learning is manual. But when it comes to deep learning, the feature extraction is automatic. So the deep learning model automatically extracts all of the features associated with that image. And when new images are fed to it, it automatically is able to tell whether the image is same to this or not. So this over here we have a graph which tells us how does performance vary with respect to the amount of data. So what happens in machine learning is that as we keep on increasing the data, the performance increases only up to a particular threshold. After that, if we increase any more data, there is no increase in performance. So this is another problem when it comes to machine learning. But on the other hand, when it comes to deep learning, the more amount of data you give it, the better will be its performance. And that again is because deep learning is based on learning data interpretation. So the more data you give it, it will automatically learn all those features of the data by itself, and it will be keep on increasing its performance gradually. Now let's look at some applications of deep learning. So speech recognition is one application of deep learning. Now you need to understand that you cannot build speech recognition applications with machine learning. So this is where machine learning fails and deep learning comes in and helps you to build speech recognition applications. Also, another application of deep learning is self-driving cars. So we see over here that the person is just sitting. He is not even touching the steering wheel and the car is driving by itself. So just an amazing application of deep learning. And then we have language translation over here. So this again is a part of deep learning. So over here we are typing something in Spanish and it is being automatically converted into English. So we also have visual translation over here. So over here this text or this board is in some random language, and this app over here which uses deep learning automatically converts this visual into English. So those were some applications of deep learning. Now let's actually understand how does deep learning work. So most deep learning methods use neural network architectures, and that is why deep learning models are often referred to as deep neural networks. So a deep neural network basically has these three models: an input layer, the hidden layers, and the output layer. And the term deep usually refers to the number of hidden layers in the neural network. So traditionally, neural networks only contain 2 to 3 hidden layers, while deep networks can have as many as 150 hidden layers. Now that's a very huge amount, isn't it? So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So all of the input data is given to this input layer, and this input layer automatically extracts the features by itself. Now that data is sent to this hidden layer which performs all sorts of processing tasks, and then the final result is given out through the output layer. So now let's also understand what exactly is a neural network. So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data, and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons, with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations, and then use the output to solve the problem. Now, as I've already said, these artificial neural networks are based on something known as a biological neural network. So, our biological neural network has dendrites, cell body, and axon. So dendrites are where the input is taken, cell body is where the processing is done, and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first we give in the data, that data is processed, and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat, and the labels would be either cat or not cat. After that, we give in a new image of a cat, and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat.
Now, there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically, artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer, known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these three main components. So we have the dendrite, the cell body, and the axon. These dendrites receive the signals, and the cell body processes these signals, and the axon finally sends out these signals to other neurons. So just like the biological neuron, the artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bias that are randomly selected. So here we have w1, w2, w3 going on till wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail. So here we have three arrows which correspond to the three inputs coming into the network. Now for these three inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the three inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to the sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have two inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have two different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these two classes. So is that really possible? Can we draw a linear line which can segregate these two classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function. Now there are many types of activation functions, and today we'll be discussing some of the widely used ones. So let's start with the identity function. So the identity function gives out the same output as the input. So no matter how many layers we have, if all the activations are identity functions, then the final output of the last layer would be the same as the input given to the first layer. And the range of the identity function goes from -infinity to +infinity. So after that, we have the binary step function. So this binary step function is usually denoted by h or theta, and it is a discontinuous function. So if the input is less than 0, then the output would be 0. And if the input is equal to or greater than 0, then the output would be 1. And this is why binary step function is used to solve a binary classification problem. So after that, we have the sigmoid function. So the formula for the sigmoid function is denoted by 1 upon 1 plus e power minus x. The sigmoid function basically scales the values between 0 and 1. So if the input is a large negative number, it is scaled towards 0. And similarly, if the input is a large positive number, it is scaled towards 1. Then we have the tan h function. It is a hyperbolic trigonometric function which scales the values between -1 and 1. So one advantage of tan h function over sigmoid is that it can deal more easily with negative numbers. And after that, we have the ReLU function, which stands for rectified linear unit. So this function will give out 0 if input is less than 0. And on the other hand, if input is equal to or greater than 0, then it will act as an identity function and give out the same value as the input. And this ReLU function is the most widely used activation function and is primarily implemented on the hidden layers of the neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane, or some hyperplane which can accurately separate these two classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here after the first iteration, error value is 2 since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function which would give us a non-linear output. So this process until here is known as feed forwarding. Now if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, they are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network. Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So today we'll cover just that. So let's start with TensorFlow. So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks
as well as recurrent neural networks. And the best thing about Keras is model building is extremely easy. It's like stacking layers on top of each other. So next we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4j. So unlike deep learning frameworks which we saw till now, which were all based on Python, Deep Learning 4j is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4j is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages, such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, and then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now this is how we can create constants in TensorFlow.
So I will use this tf and then put in a dot and then type in constant. Now inside this, I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly, I'll also create a floating type constant and I'll store this in con2. So I'll type tf dot constant and the floating value would be 3.14. Now after this, I'll create a string type constant. So again, this would be tf dot constant and the string which I'd be giving would be this is Sparta. And finally, we have a Boolean type constant and I'll store this in con4. So this will be tf dot constant and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function and then I'll go ahead and print all of these values, con3, con4. Right. So we see that this first constant is a tensor of type integer. The second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now, we have not started our session. So let's go ahead and start a session first. So I'll type sys equals tf dot session and I'll hit run. Now I will run all of these inside this session. So I will type sys dot run and let me go ahead and run all of these con1, con2, con3 and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol and then I'll take in the next constant and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type sys dot run and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions. So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant. And inside this, I will give in a list of values. So let's say I will take in 1, 2, 3, 4 and 5 and I will add this list with the next constant. And this time the second constant has the values of 5, 4, 3, 2 and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant, and this will have values, let's say the same values, 1, 2, 3, 4, and 5. Let me put a comma over here. Right. Now I'll put the asterisk symbol. Again, I'll type tf dot constant, and I will give in the list of the values 5, 4, 3, 2, and 1. Now I'll hit run. Again, I need to run these two inside a session. So sys dot run. Let me put in addition over here. After that, I would also need the multiplication value. Right, so this is our result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6s over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant, and the value of this constant would be Tensorflow. Right. Now I will run this, and let me execute this inside a session. So sys dot run of str1 plus str2. So the result which you get is I love Tensorflow, right? So the first string is I love, and then there's a space, and the second string is Tensorflow. So when I add these two strings, the resultant is I love Tensorflow. Right, so that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax, and inside that we just give the data type of the variable which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A, and tf dot placeholder, and this would be of integer type. So tf dot int 32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So sys dot run, and I want to see the result of b. So I'll put in b over here. Now, since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder a over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be a, and the value which I'll be giving to a would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to a. And when we multiply this 5 with 2 over here, we get the value of b, which is 10. Right. So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now, similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4, and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8, and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name. And this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name. And let's say the value of the string is I am. Alright. Now let me run this and I'll execute this inside a session. Sys dot run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, so let me create this placeholder. I'll name this as str name, and since this is a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type sys dot run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1, and we can create a variable like this, tf.variable. So guys, you need to keep in mind that this v over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20, and this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer. And when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So sys.run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable. Sys.run var1. Right. So we have the result of var1, which is 20. Now, since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right. Now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1, and the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update, and the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run right now. Let me run this inside a session. Sys.run, and I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here, and this is how our linear model would look like. Wx plus b, where w and b would be variables and x would be a placeholder. Right. Right, so let me start off by creating w. So w is a variable, so w would be equal to tf dot variable, and I am initializing it with a value of, let's say, 10, and this is of integer type. So this would be tf dot int32. Now similarly, I will also assign the value for b. So b is also a variable and its initial value would be 5, and this is also of integer type. And finally, we have x, which is a placeholder. So x is equal to tf dot placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf dot int32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals tf dot global variables initializer. I'll hit run. So now I will create a session. So sys dot run, and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Sys dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
So let's go back in 1980s. There was this crazy guy called Dr. Hilton. He proposed that we could mimic somehow the mind, how a human mind works, and we can mimic the way it works. so that we can also try to make a thing out of it, so that whatever our mind is doing artificially, we can also do that thing. So he proposed a paper, and everybody said that, Hilton, listen, you are doing something wrong. This is not what is right. And everybody, didn't like uh, the way things were going on. But after 20 years, almost in like late 90s, around 1999, he again came up with this paper. He brought in his paper, but this time with a proof, and he won a contest that is called ImageNet in 2004. This time he came back and everybody had to listen. So we were at 2004 when he won the ImageNet. I have two people who I've already told that ImageNet is ImageNet is actually in a competition. It is held by a uh, joint vision of Stanford plus Princeton University. These guys come up and they downloaded a corpus of images. Now they have a very large collection of images, around 1 million images, around covering 1,000 categories. They have. You can just click on explore and you can see this tree around here. So what you have to do is that you have to make a model out of it so that you can classify the images. So people used to make, hand coded, classifiers, and they were working. They were working, but at some stage, they had to fail, because like now, let's say that fish, you are trying to detect a fish, but fish cannot every ways be in the same manner in which you are building the hard coded thing, right? Or let's say that you are trying to detect a cat, and then you say, okay, top right if it is a eye, top left it is a eye, and then it's a squishing mouth, then it's a cat, right? But now the cat face will not always be available to you in that particular fashion, right? It might be a top view, a side view, a bottom view, any view might come up, and at that time people used to fail. But in 2014, 2004, when Geoffrey Hilton came with his paper, the competition he won was with 94% accuracy, and that was never achieved, and it surpassed the human accuracy also. So that was where, when people started listening to him and he came out, then he proposed slowly that, okay, that this is what I think, that artificial neural network is nothing, but that we are trying to mimic what is happening in our own mind, right? So if I say that, what is the theory, what Geoffrey said about neural network, is that he said that an artificial neural network is a computational model that is inspired by the way biological neural networks in our brain human information possesses, right? So I mean, most of you know this thing, that that our nervous system is made up of axons and okay, I'll show you the photo, that it is made up of axons and brains. I show you the photo and you might be able to. Okay. See, this is actually how a human nervous system is. Most basic diagram, and everybody of you might have seen this. So how this works is that there is a exact replicate copy of this. If I copy this, and you can attach it back here again. So these are the axon terminals that are connected to dendrites again, and this is how it flows. So let's imagine that your fingertips where you can have your dendrites, and these are like small particles again of your pure neuron connected to your brain. So this is how there are like millions of these connected, and they're connected. If I take this, okay, one more feature of Jupyter Notebook that you already know, that you can add a markdown language. So what I do is I do escape M, and then I'll write HTML inside it. So I write img src is equal to, right? This is how you can write your, in this you can add that this is right. Let's now look at it one by one, slowly, slowly. Okay, so these are called dendrites. These dendrites are the one who are like septicles. These are the one who are responsible for catching all the information and sending it forward to the nucleus. Now nucleus processes this thing and it sends to this axons and again throws it out to the axon terminals. Now imagine again that this is this copy, this is again replicated here, back here. So you can imagine that these dendrites are connected to these axons, right? And then they're flowing, 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 flowing. Now imagine, let's say that you touched a very small, a very hot glass, right? The moment you touch the hot glass, the dendrites at your fingertips, they sense that something is very hot there. So they send this information to your brain, okay, that this is hot. Now imagine this dendrite is processing the information, sending it to terminal, terminal to dendrite, then dendrite to terminal. It goes on, goes on, goes on until it goes to your brain. Now the brain says that this is very hot. You should remove your hand. Okay. Now this process is again flowing back to the dendrite, the original dendrite here. Let's say that this is the original dendrite here. Okay, and the brain will say that this is really hot. You should remove the fingertips from the glass. And now when I'm saying that this information is going on, believe me, from your fingertip to your brain, there are like millions of these dendrites who are connecting and flowing this information. Now again, a process of reversal information flow is going on, and this time your brain is sending a signal that remove your hand from the glass, and this is again going back to the fingertip, and then you release your hand from the glass. But in real life, when you touch the glass and when you remove it, how much time do you take to remove this? It's just some nanoseconds, right? I mean, less than. Your reflexes are very strong. You just remove the hand out. But imagine what is happening when you do this. Your brain is not, your hand is not taking the decision of removing that. You might think that, okay, my hand is taking the decision to remove that. No, the hand is like a slave of brain. So every body part of ours is like a slave of a brain, right? Whatever we are doing, it is sent by the brain. The information is sent by the brain, and then it's doing. This is how your body works, right? So it's a slave of your brain, and the brain sends the information, remove or attack, whatever it is, then it reacts. But it's really fast, right? Similarly to this way only, Joffrey said that, okay, this neural network, this is how even I will also build a neural network. Now I'll show you how a basic neuron looks like. Here it is. This is the image. You write it. Basic neural. It's not a network, it's just a neuron. But this is an artificial neuron. So Joffrey said that, okay, this is how I propose. Let's do the following. Let's say that your hand is not doing anything. Your dendrites or your nervous system is not, this basic neuron is not doing anything. Imagine that it's doing nothing. But it is reciprocating the information. But how it is reciprocating the information? By activating itself. So when you touch a hot glass or something, it activates itself, and then only it's transmitting the thing, right? Now imagine if this would have not activated, it would have sent nothing, right? So this is also playing a very crucial role. See, brain is sitting somewhere like a million neurons far, right? He doesn't know what is happening to your hand until and unless this neuron is sending the information. So what information will the brain process if it doesn't have the information? So these guys are very much responsible for sending the information, and they send the information only when they're activated. So this dendroid will become, this nucleus will become activated, then only it will send the further information. And see, there is also a basic kind of a information processing is going on. It doesn't mean that these dendrites are just sending blank signals. See, I'll tell you more depth inside. See, these dendrites, they collect the information. These dendrites, they collect the information and they send it to the nucleus. Now, nucleus thinks that should I process this and send it forward? Yes or no. Depending on that, nucleus send it further. Right. Now, how is nucleus sending is? Nucleus has a particular threshold value. After processing it, it says, okay, if I am activated by that processed value, it will send it further. If not, it will keep it to itself. So this is also how a basic artificial neuron when I say artificial, it means that the one that we are building right now in deep learning, right? This is also built. Now, what is happening is that imagine this round thing that you're seeing is the nucleus. This thing is a nucleus. But this is a nucleus, right? And these are the dendrites to it. This one, this x1 and x2. This is the way of thinking how we are intimating, and this is the tail, axon tail, and it is again connected to again a neural network. So it's a chain of multiple neurons going on. Now, if we go mathematically, what is happening inside this? It is nothing but a linear combination of all the inputs with a bias. I just like went to the very human biological way and I just sent the sentence. It's doing nothing. What it's doing is that it collects the input. Let's say that you have two inputs. Let's say that you have two inputs, x1 and x2. These are your two inputs. Now to every input, you will give some weightage to it. Let's say our weightage is here. This weightage is called W1 for x1 and W2 for x2. Correct? Now what I said, it is trying to build a linear regression, right? So what it does, it multiplies the weight of the corresponding input to itself. So W1 x1 plus W2 x2 plus it adds a bias to it. Now you will ask what is a bias? I'll say imagine that there is another input called x0. There is another input called x0 and the value of x0 is equal to 1. The value of x0 is equal to 1 and there is this weight associated to it that is called w0, right? So this bias is added to it and then you add this. That's it. You plus all these values, multiply plus all these values and you give this output to something called y. This is all a neuron does. Make sense? Any questions? Please ask. It's very important that you build the intuition that what is happening here. So this is the most basic, it's the smallest part of a neural network that you can pick. And the smallest part of a neural network is doing this. Like it takes all the inputs that are coming to itself, give them some weightage, multiply the weightage to the corresponding input, and then sum all these, and then add a small bias to it also. That's it. Over. How is this weightage and bias being introduced? That who is okay, x1 and x0, x2 and x1, I can say okay, someone is giving to us the input that what is the temperature of the glass. Let's say it is coming from the outside environment. X1 and x2 is coming outside, but who is giving this w1 and w2? So okay, so the answer is that in a artificial neural network environment, at the very first instance, they are randomly allocated to it. So see, you all guys have learned ML, right? So how does ML work? ML says that I know the output and depending on the output, I have to give some weightage to these inputs so that they can give me the output. Now you know that the output will be Y. You know that the output is going to be Y, right? Now you want to make some equation where Y is equal to x1 plus x2. Okay, and now this is not the correct answer, right? X1 and x2 will never give you y1. So what you do, you add some w1 here, some random w1, and then here random w2. What it will do, it will not give you the answer. W1 and W2 will not give you the answer. You will do some corrections again in W1, W2, and ultimately it will give you Y. So this is what is happening. At the very first instance, you will take W1 and W2 as random. First is that does the process is reverse? Yes, it also reverses itself. The model will not only go from x1 x2 to y, but it can also come back from y to x1 x2. And second, let's say that he's asking Shivam, does it process recursively? Recursively, just imagine that there are like thousands of, now I'll draw it again to show you. This is just a very basic one, right? Now imagine what is going on here is that this is the small that you saw, right? X1, X2, and it is giving some Y. Now here it is again, there is a X1, X2, and then this is giving me Y. Now this Y and Y1 will become an input for some other cell. And then it is giving here. So are you imagining how will it look like? This becomes this, and this will become again an input for some other. So these are like connected. These are like throwing information from one to another, one to another, one to another, right? But this is how it works. This is how a small a network looks like. And this is if I write down the theory, it says that the basic unit of computation in a neural network is a neuron, or often called as a node, right? And came right it very right. This is called a node, or you can say it a unit also. So it receives input from some other node, from an external sources or external source, that I was saying right also, right? Each the x1 and x2 might be an input from another neuron, or it might be given to you directly from the external environment, right? Computes the object each input has an associated weight to it, which is assigned on the basis of its relative importance to other. The node applies a function f to the weighted sum of this input, right?
So we'll be having the students' data. So whatever the marks, based upon their marks, so we have to decide the grade. So we have to adjust whether the student is passed out or failed. So we will be adjusting the marks based upon the grade.
This is a very hard-coded problem, I think. But let me take an example that you're working on a machine learning problem where you are trying to find out the loan defaults, right? That in bank you have multiple people who take the loan. Now the bank wants to know how will this person repay the loan or not, right? Now you already have a historical data with you. The bank will give the data to you. Okay, let's say that this is the data with you. So in that data you already know that if this is the feature of a person, this is the credit history of the person. Based on that, they will also give you that, okay, he paid, he didn't paid, he paid, didn't paid, right? And based on that you adjust your model, right? So there also you have a x and y with you. You will have your x and y with you at that particular instance also. Okay, so everybody gets this this function thing, right? That's how this function is working. This function f is called the affine. So the f function that you see, this is called the affine thing, and it's doing nothing, right? You saw that this is it's doing a linear thing here, just multiplying the weights the corresponding x1 x2, and you might now consider x1 x2 as the importance feature. So the more important x1 is, the more higher the value of w1 will be, right? The more lower the value of w2 is, it means it doesn't make much sense to y. So everything that we will now talk will be with respect to y. So the x2 is not making much sense to y, so the value of w2 will be very less. Let's say y is dependent on x1, so this value of w1 will go more higher, right? And then your bias you already have, this is a static thing, right? Because the x not associated to it is equal to 1, right? Let's now go back at what further happens here. Now you get the y out of here, right? Now this y thing is a little, you have got the answer, and this might be greater than 1 or less than 1 also, right? So there is no measure of this answer. It might happen that w1 w2 is very small. Let's say w1 w2 are very small, then the value of y might be almost equal to 0, right? Or let's say that w1 value is very high, like very high, so the value of y might also get very high, right? So now this might bring some bias, this might bring some ambiguity to our model. This y might be sometimes, next to infinite, it might be equal to infinite, or it might also be equal to 0, right? Depending on the variables. And we don't want that. We want our y to be in some particular range, right? We want our y to be in some bonded weights, right? Then comes next guys whose names are activation functions. Activation functions. Now we got to know that how this y is made, right? How this y is ultimately achieved. Now to adjust the value or squeeze the value of y, we need some other thing, right? We need something that can control the value of y, and these are called activation functions. Now what activation functions does is that they will take the value of y and they will squeeze the value of y in some certain range. What they will do, they will squeeze the value of y in some certain range. So we have multiple, let's say we have a step function, we have a 10h function.
Shivam, Sanjay said, can you please come again about this activation function? Not getting you properly.
So let's come back what this activation function is. So you understand that the value of y, how it is calculated, right? It is now totally dependent on w1 and w2. If the value of w1 and w2 is very less, I mean 0.0000 or let's say 10 to the power minus 23, then the y is going to be very less, right? Next to 0. Or let's say that the value of w1 and w2 is like 10 to the power positive 48 plus 48. So this might be very high. The value of y might be very high. There might be no standard to control this value of y, right? Mathematically, there is no, this value can go from negative infinite to positive infinite, right? And this is not a very good range to get about a particular output, right? So what we do is we introduce something that is called activation functions. Now what this activation function will do is activation function will make sure that your output that you have got y should be in some particular range. What it should be? It should be in some particular range. Now how do you decide that who is going to be in what range, and how is that range called? See, the activation function, if I ask you mathematically, the mathematical purpose of introducing an activation function is to squeeze the value of y between some variable called 0 to 1, right? Majority times. So the purpose of activation function is to bound the y in some range, right? And this range might be minus 1, say 1, 0 to 1, or sometimes 0 to infinite. It might be different things, right? I was at this thing that mathematically the value is to be squeezed between 0 to 1. But if I talk to you about statistically why I am doing this is, now imagine till here, till this particular range, your model is a linear model. Everybody agrees with me, right? This is a linear model. Nothing non-linear have been done till now, right? All the things that we have done till this step in this circle, everything is linear. There is no non-linear thing, right? Now, linear things are a little bad at classifying things if there are more than three classes, right? If I ask you, can you, if let's say there are three classes, one is like crosses, right? One is circles, right? And one is some triangles. Now, can you make a single line and can divide these three data? No, right? If it would have been two classes, you might have drawn a single line and you might have divided the data into like two classes, right? But if it is a three class data, how will you divide this? You have to ultimately make a triangle kind of a shape, or this kind of a shape, right? Then only you can divide the divide this thing, right? So I'll show you a photo also. Let's say, let me give you an example, then I'll show you how this works. Okay, can any one of you, let me hide it here. Now this is this thing in front of you. Everybody can see your data. There is this red dots and there is a blue triangle in the screen, right? Everybody can see this. Now, can you make a linear model that can separate these two things? This can only do in a two dimension, right? But if I say you that, okay, see a magic, anybody wants to try this thing? How will you do? No? Okay. What I'll do is I'll remove this now. So what I did was I introduced a third dimension, and now I could easily separate by introducing a hyperplane here, and then I can say, okay, something that is above this hyperplane is red, something that is below this hyperplane is blue. Makes sense to everyone, right? So this is why we do activation function, to make sure that we want to classify things more better, to make things more clear. We do an activation function. So mathematically, why we are doing activation function? Because we want to squeeze the value of y somewhere. If I talk statistically, what we are doing, we are introducing non-linearity in a linear model, because linear models are very much not capable of classifying things in when the number of classes increases. So now we saw that as soon as we increase the linearity, if we increase the dimension in the data, if we introduce non-linearity in the data, what it is doing? It increases the chances of making a linear separable model, right? Right. So if I say in three times, first mathematically squeezing the y. Second, if I say graphical thing, why we are doing this? Because we want to introduce a new dimension. And statistically saying why we are doing this, because we want to introduce non-linearity inside it. Now you might be asking what these functions do. It's a very good question. I have activation functions graphs. See, this is how a sigmoid looks like, a tanh looks like, a ReLU looks like, and see everybody is bounding. So see, sigmoid is bounding between 0 to 1, tanh is bounding between -1 say 1, ReLU is bounding from 0 to infinite. So it lets go everything that is going above. Yes, we have step function also. Step function says that you can go, if something can be only have two things, either 0 or 1. If something is negative, it goes 0. If something is positive, it goes 1. It's a step function, sigmoid, tanh, ReLU. So there are multiple things. These are doing the same thing that we want to do for a activation function. ReLU, you can understand that if something is negative, it says it's a 0. And if something is positive, it lets go whatever the value of this is, right? I write the variables in here. This is what brings in. Sigmoid is this, tanh is this, and ReLU is this, right? What is the maximum of 0 to 1? That ever value it will take, right? This is what activation functions is. Let's say that you have this thing called y1 and y2, right? And now the value of y1 and y2 is very large, right? So this y3 will become ultimately also very large, and this y4 will become also very large. And we know this is not the exact thing. We always expect our output to be in the form of 0 to 1 if it is a classification problem, and if it is regression problem, then it will always be in some range from 0 to 1, right? You all agree with me, right? In machine learning also, whenever you did a classification problem, you one hot encoded the problem. So you never said that the output is going to be a C80 cat or DOG dog, right? You always said that, okay, if 0 comes, this is cat, 1 comes, then it's a dog, right? You did the same thing, right? In machine learning also. Or if it was a regression problem, then you always regress a value from 0 to 1 with a multiplicative factor, right? So this is what is happening here also. The y3 and y4 ka value can never go up beyond a limit. To control that limit, we have to squeeze the value. And see, when I'm saying squeezing the value, that is in mathematical format. But if you see in statistically, what we are doing is that we have to introduce non-linearity into the data, right? Because linear data are not, linear equations are not good in separating non-linear data, right? Right, this becomes separable. You see, now it is very much separable just by a simple hyperplane. Okay, so coming back to a feed forward neural network. So see, this was the input x1, this was input x2, and now what a feed forward neural network expects is that a hidden node should be connected to all the inputs. What does it expect? It should be connected to all the inputs that are in the previous layer. So this is, let's say this is called layer, input layer. Wherever your hidden neurons, this is called hidden layer. And your outputs are here. This is called a output layer. Now when you are building this feed forward neural network, your responsibility is just one, that whichever neuron you're standing, let's say we are standing on this particular neuron, let's say this neuron, this neuron. Now the only thing that this is not a neuron exactly. Oh, sorry. Let's say we are standing on this neuron. Now the responsibility is just this, that if you go to the previous layer is the input layer, all the neurons in this layer should be connected to this hidden node, right? Similarly, output 2 also expects the same. You go to the previous layer. So this is the output layer. What is the previous layer? Hidden layer. So all the neurons in the hidden layer should be connected to the output node 2. Make sense? Or if I make it more easily, let's say that whichever neuron you are standing, just go to the previous layer, and all the neurons in that previous layer should be connected to this particular neuron, right?
What is this layer signifying here?
Correct. Very good question. So what you are doing is you have stacked all your neurons one by one in some format, right? So all your input neurons. So see, whatever you made in this above statement here, in this above thing here. So this x1 and x2, this is x1, x2. This might be x3, x4, x5, x10, right? So these x1 and x2s are what? Inputs, right? So what you do is you collect all these and you just put it inside a layer here. This becomes a hidden layer. Now you will not only have one neuron, you will have multiple neurons, right? So what is happening is that what you have done is, rather than having just one neuron, what you have done is you have made multi-neuron system. So this is a feed-forward multi-neuron model here. So what you are seeing in the previous photo, that is the image that I showed you, that was just a multi-input single neuron. But now you have multiple neurons. So what you do is you stack these neurons in this layer. Then you can have, so this is just an example. What you can do is you can have an image like this also. Multi-layer. Okay. So now if you see Tarun here, so what is happening is these are your inputs x1, x2, x3, x4, right? This is your input layer. This is your hidden layer 1, where all your affines and activations are happening, right? This is your layer 2. Again, all the affines and your activations are happening. And this is your output layer. Hidden layer HL2. This is HL1. And this is input layer. So what is happening is that, let's say this is called neuron 1. That Y1 just marked. So let's say this is N1. This is called neuron 1. Now what is happening is that this neuron 1 is connected to X1 also, X2 also, X3 also, and some bias also. So what is happening here? This affine will be happening here. What will be happening? It will be here that W1 X1 plus W2 X2 plus W3 X3 plus some bias B will give some output called Y. And here you will be having a very small activation function also residing here, right? Similarly for this N2 also, this N2 is connected to all the inputs, right? This N2 is connected to all the inputs. This N2 is connected now. It is connected to this, to this, to this, and this. Now N2 will also do some affine and then bring some small activation function here, and it will also give some output called Y2. Similarly, Y3 will also be here. Now this Y1, Y2, Y3 will become input for these neurons. Let's say we call this neuron as N4. Now this N4 is connected to this, this, and this. Similarly, again affine, and let's say it gives the output called O1. Now O1 is here. Similarly, O2 is here. Now this O1, O2 will also become input for this. Let's say we call it O1 right here, right? This is O1. Y4. Let me remove this. Sorry. We were here that there is this some output called Y4, and there is some output called Y5, right? Now what is happening? Y4 and Y5 will become output for this O neuron, and they will give some output O1 and O2 similarly here, and then you will have outputs, right? This is how a multi-layer neural network works.
How will we know that how many layers?
Correct. This is one of the very good questions that first of all, how many layers do you want? This is the layers that you have, L1 and L2. Now you might have another question that okay, in one layer, how many neurons can I fit? So there are currently four. I can fit 5, 6, 10 also, right? I can fit 10 neurons also. So who is going to tell me that how many neurons and how many layers? This is what data science you are going to do here. I mean, everything is built for you. This neuron thing and this all thing is this is already built for you. The only thing that you have to do is that you have to come up with the optimal number of neurons and optimal number of layers for each neural network. And now who is going to decide this? Very good question. This is you who is going to decide this. And how? Okay. So first answer is that hit and try, that everybody will tell you, and I'm also telling you that the first approach is hit and try. Let's say that you are doing a very new problem. I mean, you don't have any idea, you are just doing. So one thing is that you'll go with the hit and trial model. Second is that as soon as you become a little bit expert, now you start learning, okay, this is how my model is reacting to this particular neural network layer. Then you see the model capacity. Okay, so let's say that, so see, this is a very good question, but this is also an advanced question. Now see, when this, let's say this is called neuron 1. When this neuron 1 is connected to x1, x2, x3, there is a weight called W1, W2 on this layer, and W3 here, right? So, but when this N2 is connected, this is not W1, W2, W3. There is W4, W5, W6. So when this x1 is connected to this N2 here on this line, there is another weight, that is W4. So imagine how many weights are there for 3 inputs, 3 neurons. There will be 9 weights, right? Now there are 9 weights. Now imagine here again that you have 3 inputs and 2 outputs, 3 to 6, then you have 6. So 9 plus 6. Then again here 2 to the 4. So you will have 2 plus 4. So 9 plus 6 plus 4 is 19. So 19 weights are there, and then you will have 3 biases here, right? So 19 plus 3 is what? 22. So for the small neural network, you have 22 values that you have to predict, right? Because y1, w1, w2 we have taken as random, right? And biases are also random. So you have to adjust them in a very optimal way so that you can get the output as y. So now imagine that you have 22 things that you have to train here. 22 things that you have to predict, not predict, but you have to optimize, right? And now let's say that you have a data only for like 10 rows. Now, does this justify that you will have 22 things to adjust in the 10 rows of data? So this is called capacity building. So what you have to do is that you have to check your model if your model is even capable, if the data is even capable to adjust these values, right? Let's say that you are just doing a simple addition, right? If you give two numbers, your model has to give some output, right? Now let's say that you have 1,000 examples for it, but now you're building a like say 1,000 layer and 1,000 neuron per layer, 1,000 neurons, and then you have 1,000 layers. Now does the model require this much of data? No, the data will be lost in some third or fourth layer only, right? And see what I just said in just last 2 3 sentences, this will come slowly with the experience in you also. So what you'll do, so whenever a new problem comes to me, I first of all read the research paper through it. See, because we are not researchers. Let me be frank with you. We are not researchers who are going to make things. We are deep learning engineers here, right? We have to implement the engineer and we have to solve a business problem through it, right? So what you do is first of all you read some papers out of it, right? Then you get the intuition of how do you build a neural network around it. Then I do some hit and trial error. Okay, this is how you build, and this some changes, and then slowly you understand. Okay, when I change this thing is affected more. Then you reduce and more. Then you have some prior knowledge also, like that I told you. Keep capacity. That what is the capacity of the model? Let's say that you have a very large data, but you are just building one layer. Then the data is underfitted, right? Or let's say that you have very less data, but you have made a very big neural network for this. And this is called overfitting, right? You have a very over number of neurons for your model to be predictable, right? So slowly you will you will have intuitions, and this is, I will tell you, with your when you will be doing your first problem in a neural network, you will understand slowly See, you might be thinking that, I'm not taking to you practical, right? I am not telling you about any real world example, but this theory is really important. I might directly jump to the code also, but that will make no sense to you after 2 or 3 weeks, right? Because code anybody can write. Until unless you don't know, okay, what will happen is the next, after 2 or 3 months, when you will be making your own neural network, you will fail that, okay, which activation function to use. Then this thing will occur. Okay. So see, this is what he is talking about to all the people. This is what he's talking about. Let's say that you want to add more layers. So currently there is only 2 hidden layers. You want to add more, add more, add more, right? If you want to increase per layer, you want to increase the neuron, you might go like this also. Okay, you might like, I'll reduce it to like, let's say 6. This I'll reduce it to 4. This into and this is 1, right? This is how your neural network will look like. These are the two inputs. Now every input is connected to the every neuron in the first hidden layer, right? Then second, then third, then fourth, similarly. And this is how the data is flowing inside it. You can see now slowly. When we put every X into each neuron, does every neuron give same Y? Very good question. But no. See, Kim, if we come here, it would have been the same if they would have same W, right? So if X1 is connected to N1 here at this layer, it has W11, right? But when X1 is connected to N2 here, it has something called W12, right? So there are different weights. So it is coming from X1, but because it is connected to different neurons, different input neurons, they will have different weights also. Understandable? So to other people, what Kame is asking is that, okay, that you are doing affine. I understand that you are doing affine, but let's say that, let's go back to affine equation. Because the value of x1 and x2 is constant, the output will always be constant, right? But no, because y1 is made up of this equation, and this equation is also driven by w1 and w2, and the w1 w2 values are different, the value of y will also be different in each case, right? Makes sense, right? And when you are asking about a real world problem, this is how a neuron will work. Okay, I have this also, don't worry.
So you mentioned overfitting and underfitting neurons,
Yes,
so how do we come to know that based on the Y or
again a very good question. So I took these two words called underfitting and overfitting. This is how it actually works. This is a intuitive GIF. Okay. So what Suresh is asking is that, that I took two words in overfitting and underfitting, and how do we address this problem? So what we do is that we divide our data into two parts, and I think you must have also done this in ML also, right? Training data and validation data, right? Not two, just three parts, right? Training, validation, and testing, right? So what you do is whenever you are training your model, you just make a slice, another slice of data, and this is called validation data. And you will never show this data to the model, right? So no, you are never going to train your model on this particular data. So what you're doing is you will never show this data to the model, so model will never come to know about it. So it will never learn about it also. Now once your model is made, what you will do is you will test it on this data. What you will do? You will test this on this data, and then the model will say, okay, this is how it looks like. Okay, this is what the predictions are, and then you'll see the predictions, and then you'll compare the predictions. Okay, this is not what I wanted, so the model is underfitting or overfitting. Now how will you do underfitting and overfitting? You'll do a confusion matrix, and then you'll see that if the model is just giving out you only one classes, let's say that your data had 10 classes, and if the model is just pushing towards one class, then this is overfitting. Your model is overfitted at a very lot level. Okay, then we have another question from Game. He says that it means, now this dog image, when we expand this image mathematically, this will come out to be three things. One is called x1, x2 and x3, right? Now what we have to do is this x1, x2, x3 is done towards from our end. Now this x1, x2, x3 is connected to this neuron 1. Okay. Now x1 is connected to n1. This is called w11. But when it is connected to n2, it will have some another random weight called w12. w12. Make sense? So number of neurons you can increase as much as you want. As much. You can have n3, n4, n5, n6, n7. Doesn't matter. But you have to make sure that this w11 is not the same weight for all n1, n2, n3. Right? Cool. Thank you. Thank you. So inside the matrix, you can see there are multiple values. The value ranges from 0 to 255. 255 is for like utter black and 0 is for white. Right? The value ranges from 0 to 255. You can see the more black it is, the more the value it has. Right? So what is happening is that these are the multiple inputs that you will have inside your images, multiple inputs, and all these inputs will go in here. So in this particular example, you are seeing 3, but this time you will have more. So these all the zeros in first, all the values in second, third, fourth, fifth row till the 28th row. You will have all the numbers inside this input layer stacked one by one. So ultimately you will have 28 cross 28 is equal to 784. So you will have 784 inputs normally for this small image. And this is you guys were all asking about me how this will work in real world. So real world, let's say that you have an image of 500 cross 500. So that becomes around like 25,000,000. That means 2.5 million inputs you will have for single image, right? And let's say that you have 10,000 images, so this becomes multiplied by 10,000, right? So these are the number of inputs that will go inside one by one by one by one by one. So one image will go one time, two image will go two, second time, third time, and then based on this, the output is the model is going to do some calculations in the hidden layer, and then it's going to predict the output, and it will give you some output at y. Okay, so now we'll turn up pages and we'll move to multi-layer perceptron. But now we might have multi-layer perceptron architecture. Now a multi-layer perceptron architecture simply means that you might have multiple hidden layers. Okay, so apart from having a input layer and output layer, you might have hidden layers in between of them also. Whereas a single perceptron was only a linear function, a multi-layer perceptron will have multiple linear and non-linear functions, a combination of them, right? I'll show you this. And I was not able to continue today and tomorrow. Today also you will not be able to continue. Okay, don't worry. I'll push the notebook in there and then you can have it. Okay, so I think you already saw this, but I have a image of multi-layer perceptron also. Let me show you. Okay, so this is how a multi-layer perceptron looks like. If I just minimize my screen a little bit, so you can see this now. Again, just to memorize things up, this is x1. This is what your input, x1, x2. These are your two inputs, right? Now you have a single hidden layer right now here. You have this one neuron here. Now you already know that what is the calculation going on inside. There is the affine function. Affine function, what it does, it takes input from all the behind layer neurons, right? So if I say it takes input from all the behind layer neurons, and if this is a hidden layer h1, then it means that it will take inputs from all the neurons inside this input layer, right? So this is x1, then this is connected, this is x2, this is also connected. Now whenever a neuron is connected to another neuron, it is connected through some weightage corresponding to it, right? Let's say this is w1, this is w2, right? And then you might also have a x naught. Now the x naught is always equal to 1. So you might say this is just a bias as b. Now this b is like constant to this neuron also and to this also, right? I change this and it not come to this. Okay, So now this is x1 and x2. For this, when they are connected to this neuron, the one that is downwards, and this neuron, they are connected again to some weightage, but this weightage might or might not be equal to the W1 that is the one that is described here. The one described here, this is never going to be equal to this one, right? So these are different weights associated with different. So you might, to make it more simplified, you might think that whenever there is a string connecting two neurons, it is connected through a weightage, and this weightage is different for each one, right? This weightage is different for each one. You might also see the equation here down here, W naught in plus 1 plus W1 x1 W2 x2. Now you know that W naught is equal to 1, so we have replaced W naught is equal to 1. Sorry, x naught is equal to 1, so we have replaced x naught with 1, and W naught in itself you can say W naught, or what people like to say is it's called as notation called B, and this is called the bias of the neural network. Okay, bias, and these W's are called the weightages, right? And then you do again a summation out here, and this time you do the final output, and then you give the output right here, right? You also remember that after every neuron there is also activation function which is sitting here, here, and here. They are also present on the outer section also. This and this, they're present here also. So they, and then you read that there are different types of activation functions. Activation functions from step function to sigmoid, then to uh, softmax. We have different. I'll slowly go through each of them, and then you'll understand that how they interact, and how you might be also changing them according to your needs, right? Okay, I'll minimize it. Visible now? So now once we are done with this perceptron layer, now okay. So this is called a feed forward neural network. Just one thing, feed forward neural network. Once you come from here, this neuron, you go to here, then there some calculations goes on. Then you come to here, which is taking collections from this and this neuron, and then you give the output, right? Now let's say the output comes out to be some y1, whereas the actual output was, let's say, y, right? Now there is the error associated to it. So you say that you have an error, and what is the error? Y minus y1. This is the error, right? Y was the actual answer that should come, right? But you are saying the answer is y1. Then y minus y1 is actually the error. What it is? It is actually the error. This is actually the error, y minus y1. Now your model, you say to your model that model, you have done some kind of mistakes. Now if you go back inside your session, if you go back to your session, you might see some errors inside it, and that error might be equal to y minus y1. So go and do the changes. Now if you see our function that we have done till now, the result through which we have come till now here at this point y1, it is all how much dynamic things you have taken, I mean non-static things you have taken. See, x1 is always going to be static, right? This no one is going to change this x1 and x2 because these are given by the data itself, right? So the data can never change itself. It is you who has to change, right? Then what is the thing that we have taken assumed? These are the values of w1 and w2, w1, w2, and w naught. These are the, similarly these w's here, I mean all the w's that are here, all the w's that are here, these values are something that you have assumed, right? So now what the model says, that the value that you have assumed, w1 and w1, w0, w till wn, these values might have some kind of a correction, because the current values of w are giving some error, that is y minus y1. So to reduce this error, you go back and check your values of w and switch the values of w to such an extent so that they minimize this error, right? Whatever I said just now is statistically, right? Makes sense to everyone, right? What I just said here. Okay. Now this thing is called backpropagation. Back Now this thing is called backpropagation. Now backpropagation, if I take the copy of, then can we try different activation functions too? Yes, you might try whatever activation functions you want to try, but there are some. Okay, so Oman has asked this question that how do can we use different activation functions also? Yes, it depends on the problem that uh, uh, what functions do you want to choose. So I'll tell you my particular example. So I was working on this library that is called DOLD5. Here what we are trying to do is that we are trying to restore colors into uh, images that don't have color. So I mean, if you talk about images that are like from that are before 1924. So we have some German artifacts. Those are before 1924, and those are totally black and white images to us, right? So what we have to do is that we have to fill images inside it. Now, filling images inside it is, I'll tell you, it's a complex process, but there is a form of images that comes out. It is called the LAB images. So if someone of you who has an interest in photography uh, or if you understand what images are, then you might have heard this term called LAB. LAB images to convert. Now the range of LAB images is from minus 128 to 128. So here my task. So if generally if you see the activation function, if you remember from the previous class, all our activation function from ranging something from 0 to 1 or minus 1 to plus 1, right? Now I wanted something that has to go from minus 128 till plus 128, right? Then how will these things two go? So accordingly you can change your activation function and you make your own function out of it, right? Make sense?
Yeah, I forgot you in the last lecture you said whenever you're trying to bound your values in a certain point, then you use
Correct,
different activation function. I just reminded.
correct, totally correct. So so this is all about the feed forward. Now if you so feed forward, if I just say in one line, feed forward is going from input to output. Now if you want to come back from output to input to make corrections, that is called back propagation. Now back propagation is one of the most used, or I should say, okay, now visible. Okay, now this is one of the most not used, but this is one of the most obvious things in backpropagation. This is in AI, and why this is famous, because this is the main backbone for AI. This is how AI learns itself, right? So people say that AI is learning from itself. No, it's not learning from itself. It's learning from the errors. Whatever error it is making, it goes back and it checks. So see, a human tendency of error checking is what? Let's say that you are doing some calculation and you do some error. What do? You go back again to the calculations and you check, okay, I did this mistake, and then you correct it, right? This is also the way how machine is also understanding. So what machine does, machine does some calculation, it calculates that there is some error, then based on the assumptions that it took, or based on the assumptions it took, it thinks, okay, these are the things I assumed and this is now the error. So what it does, it goes back and say, okay, I will change my assumptions, I'll tweak my assumptions, and then I'll see what is the error again. This is a iterative process. So again, let's say that in backpropagation, what will it do? It will try to change the values of W1 and W2, right? It will try to change these values of W1 and W2, and then it will again go in the forward direction, and it will again see, okay, again there will be some error, but this time the error will be less as corresponding to the previous error, right? Now again it will go back, then come forward, again go back, forward, go forward, inward, forward, backward. This will happen multiple times, and at one point the error will saturate. The error will look like this. So error graph will look almost like this. Here error is on the y-axis, right? And this is whatever you say, time on the number of epochs or steps, let's say, as of now. Steps means that how many times you have gone forward, backward, forward, backward. So you can easily see here that that the error was very high at this particular point, but then it slowly decreased. It decreased till here, but now it's almost saturating. So it's like almost saturating. And at one instance, it will be like parallel to the x-axis. It will become parallel to your x-axis. This is how it looks, right?
Shivam, so how this program will go back and forth? Means it's APIs, or we have to manually do this every time, run the program each time, and or run the program in the reverse order? Can you make it clear?
Okay. So, so the point is that first of all, we'll do it on in our hands. So we'll do it manually first.
Okay.
But good news for you is that no, you don't have to do it manually. All these things are like handled by the framework itself.
Many times we have to go back and forth so that it is
No,
minimized,
no, no,
it
no.
become
This you have to
parallel.
decide. This you have to decide. You'll see the error graph continuously, and then you'll decide, okay, now I want to stop, or okay, no, I want to go further. This is up to your hands. Okay, makes sense, right? I mean, see,
Correct.
the what if they can even tell this that if they can even tell this that how to stop, then I think the problem is done. I mean, then we will be doing nothing, right? We just open the and we just say this is the code, read the code and do it itself. Read the problem and do it itself, right? No. The problem is that it will do everything, all the calculations for you, but the mind where to stop the problem, where to go ahead with the problem is still in your hands. You have to still make sure that where do you want to stop the things, or where do you want to again get the further out of it, right? Make sense, right? Okay, let's move forward. I have one more theory for you. Let me paste it. Okay, so don't read this. I'll tell you. This is just for your purpose, so that in the weekend, when you weekdays, when you go back and you want to, don't have to like revisit the whole video. Don't review the video. You can just read it through the notebooks only, right? That's why I'm just copy pasting the theory here also. So what happens is I've already told you that all the edges that you are hit that you see here, that all these lines that you sorry all these lines that you see here, these are called edges. All the connecting things are called edges. Now for every corresponding edge you have a weightage, right? For every corresponding edge you have a weightage, and these weightages are by default randomly assigned to you, right? Now they are randomly assigned at the very first point when the problem start. At that particular instance, these are like randomly assigned to you. Now for every input in the training data, the ANN is activated and its output is observed. This is what I told you also, right? That once we'll do all the calculations, we'll do the first feed forward neural network. We'll check what the output is, and then the output is compared with the desired output that we already know. And the already know, this is also, you might have heard this term again and again. This is called ground truth, right? So see, deep learning may you might have heard this is not equal to what traditional technologies. In traditional programming, you have been given the input and people ask you output. But here it's not like that. Here they will give you the input also and the output also. And then you have to define some way to convert this input into output, right? This is how machine learning works, right? Because they give you input also and then they give you output also. So like say, let's first on the first example, if someone tells you that you have to do some image classification problem, then this is not like they'll give you at the very first instance, this is the image, now tell me what it is. No, they'll give you a training data set where they will give you the output also. With the image, they will also tell you that okay, 9 is written here, 5 is written here, 7 is written here, right? So you have the ground truths with you also. Now what you'll do, you'll compare your result with the ground output, and then the error is propagated back to the previous layer. If you read the line propagated previous layer, the error is noted and the weights are adjusted accordingly. This process is repeated till the output error is a predetermined threshold value, or where you think that it is being saturated. Right? This is what I also told you. Now, if I tell you that how it goes, okay, let's see one by one. Mathematically, I'll show you one by one also. Now, see, it's pure maths. Okay, just a little attention, and then we'll be here. Let's say this thing is called. okay, or otherwise what I can do is I'll just pick up the smaller problem and then I'll show you also how it is done. Okay, just a second, let me search for the image that I have. Mhm. Okay, sorry, I cannot find it right now, otherwise, but okay, let's go. Let's see that error is equal to, I'll write it down. Error is equal to, let's say, y actual minus y predicted, right? Let us write down error is equal to this e. I'll write down. Okay, now if you see that how is this y1 calculated, then let's say that we had an input called, we had an input called i1 and let's say i2, write down, and let's say that we only have this one. Okay, let's make it more simple, right? I will take just this image. That will make you understand how things work, right? Let's copy this. Okay, I'll write it down. Okay, this is the example, right? So now we have input as x1 and x2, right? And we have an output called y. Let's say that the actual or the desired output be ya, right? This is what we require from them. This is how we have, and the value of y is equal to, w1 into x1 plus w2 into x2, right? Everybody agrees to this, right? That how is this calculated, right? Now the okay, and let's then define error. Error is equal to, y minus ya, right? Or whatever you want to say, ya minus y, doesn't make much problem to us, right? This is how this is working. So now if I say e is equal to y minus ya, then I can say e is equal to, instead of y I can write w1 into x1 plus w2 into x2 minus ya, right? Now if you open up this, doesn't make much sense, but let me write it down. W1 into x1 plus w2 into x2 minus ya, right? Now, sorry. Okay, now the error is this, right? Now, what do you want to do? Now the final equation of error is in front of you, right? If I write it down, The final equation is in front of you. You can now you have the final equation in front of you. Now you have to see that how to minimize this equation, right? How will you minimize this equation? This is the equation of error in front of you. Now what you can do is, now you might be thinking that okay, this error equation is just a simple linear equation, I can solve it linearly. Now imagine that instead of x1 x2 you have 1000 xn, right? Now this equation is not a 2D equation. Now this is a 1000 dimension equation. Now you cannot just simply do things and just check it around, right? You cannot just do it like that. You have to, you cannot just plot a graph and you can look into that, right? This is a little more complex than we thought of it, right? If I show you how the graph might look like, right? The graph will look like this. Don't just read this, just for the time being, forget this thing. Just don't read these things. Okay, so what I can do is I say okay, this is your error equation, or let's say error I can also say j of w. You might see this terminology j of w as error. Okay, I should not do this. This is not making it good. Okay, when you plot this thing here, now what you can see is, see, x1 is what? X1 is a constant, right? X2 is a constant and y is a constant. You all agree, right? That x1, I will put a star and say x1 comma x2 and ya are constants, right? You cannot change them. These are constants, right? They make no effect to e. The one that might change e is w1 or w2. Okay, for a fact, none of you told me, but we missed a bias also here. Bias b. We missed this bias b here, right? Say this b, but this b is, I mean, it's not going to make some effect to us, but still, just for the courtesy, let's put this, right? To anyone, any doubt is still here, please ask me questions, right? So now we can see that okay, what is happening is that e is only dependent on w, right? E is only, the error is only dependent on w1 and w2 and b. None of the other people are changing this e. So what we'll do is we'll try to plot this error with respect to the weight, and we'll see this is how the graph looks like. And what do we want to do with the error? If error is y minus ya, what is our aim? Our aim is to make ya is equal to ya as equal to y, right? This is what our aim is, right? If ya is equal to, then we are saying that the error should be equal to 0, right? Error should be equal to 0 or tending towards 0, right? But if I say mathematically 0 is, if I say statistically, this error is never going to be 0, right? This is never even tending to 0. So what our main focus is? Our main focus is that if e is here, our main motto is to minimize the current error. Whatever the error is, we have to minimize this error. Now the value of this error can be found here, right? You can simply see the graph and say okay, this is the value of e. Just take the value of w's and plot them, right? But as I told you, now these errors are not just two inputs. We have like 1000 inputs, so we might have 1000 w1s and then one b also. So we cannot just plot it. So it will become a 1001 dimension graph. You cannot just plot it. So now we have to think mathematically that how can we minimize the error e. Now minimizing the error e, but we also have the like the equation of e also. We have the equation. Don't think that we have the graph, just think that we have a equation of e also, right? This is above, right? An equation of e is somewhat like this. If I copy this from here, this is somewhat like this, right? This is somewhat like this. This is what the equation of E is, and this is how we have to minimize. Now, in mathematics, we have learned, in inferential mathematics, we have learned that if you want to minimize any curve, if you want to minimize any polynomial curve of the order greater than 2, what is the process? Can anybody tell me? If you want to find out, if you want to know that where is,
First
yeah,
derivative, I believe.
I'm sorry, what?
Take the first derivative
Take
of
the
that
first
first.
derivative. Okay,
Yep.
okay, correct. Take the first derivative. That's very much correct. So as Omar said, that you have to take. So see what the first derivative tells you. The first derivative tells you that wherever there is a change in the slope of the graph. If I talk about what we learned in our higher education about differentiation, was the differentiation tells you that point coordinate where the graph changes its slope from positive to negative or negative to positive. So if you take the first derivative, it will tell you this place. See, it was in negative slope, then it came in positive slope. Now again here, when it was in positive slope, then it came into negative slope. Again positive, negative, positive, negative, positive, negative, positive, negative. So it will tell you all the places where it has uh, changed the slope from positive to negative or negative to positive. Vice versa, it's possible, right?
Yeah, but
Sorry.
like for global minimum and maximum, you have to take the second derivative instead of the
Second
derivative.
derivative. Correct. So this was how we talk about inferential mathematics. But if you go in descriptive mathematics, it says that what is a derivative of a function? A derivative of a function when you have a tangent that is parallel to the x-axis, right? When it is parallel to the x-axis. So how where will be the tangent parallel to x-axis? Whenever there is a slope that is equal to 0. So if the slope was from positive to going to negative or negative to positive. So both the mathematical percepts tells you that there is a change in the slope in that, right? So similarly, we can know that where are the positions, where are the places where we can get a change in the slope. Now, as Omar very he suggested that we will get all the points where it is maximum and minimum also, and we just want the point where it is minimum. I mean these points, we are interested in the one that are by dotted by green, either this, either this, either this, right? But now again there's a problem is that these are very higher error. This one that I'm just marked as E1, this is a very higher level of error, right? We don't want a higher level of error, we want a lower level. This one we want the E3, we want E3 to be our error. So what we do, we take double differentiation. We first take differentiation, then we take double differentiation. Now double differentiation, then Omar, can you tell me what is the condition? If it is less than equal to or equal to less than 2. Okay, I'll tell. Now, with the first derivative, you can know that where is the slope of change. But if you want to know that what it is, if it is a maxima or if it is a minima, how do you know it? You know by doing a double differentiation of that thing and then checking its dimension. So if the double derivative of any of your function is greater than 0, if the double derivation of a function is greater than 0, then it is a minima, right? And if the double derivation of any of your function is less than 0, then that is maxima. These are the conditions. Then you will check accordingly and you will go for minima. Now again the problem is that okay, now you will reject these points. You will reject all okay. So you might discard this, you might discard this, you might discard this, you might also discard this, right? So you will remove all these blue points. Now you will only have the green points with you, right? Now you want this E3 to be there, right? Now we don't have any mechanism through which we know that we have reached global minima or not. This is the dilemma in deep learning. And so slowly what we do is now understand this mechanism. This is called this whole thing that I'm showing you right now is called gradient descent or GD, right? You might have also heard this as SGD, stochastic gradient descent. When you do a gradient descent in batches, it is called stochastic gradient descent. Okay, I'll take a pause here and to anyone who has not understood this thing, please ask. I know I might have taken a very quickly this up, and again one more point to other people also who are not math heavy. See, this maths is just for your understanding. You won't be doing all this maths in your programming. No, you won't be doing all this in your deep learning courses. You will be just writing the direct code. You won't be doing all this mathematics. This is already done by the framework, so don't worry about this. But again, my point is, please try to get this inside, because this is necessary, right? This is necessary. If you don't understand what is your framework doing, then there is no sense of your framework doing something, right? So uh, just please, and if you have any doubts, please ask. Please ask. Do not hesitate, because I know it took me 3 days to understand this thing. So I was, how do you put, okay, so I am assuming that everybody understands till here. Okay, so what I'll do is I'll take the first derivative of dE, sorry, dE. Now you know that E is equal to this. Let's write it down. So now you have seen this one thing, that now the E is dependent on either W1 or W2. So what you'll do is you'll take the derivative with respect to one time with respect to dW1. So what will happen? It will say x1 and then everything is equal to 0, right? Because these are all constants. Am I correct or wrong? What I'm doing is I'm trying to take a derivative with respect to W1. What will happen? X1, correct. X1 into 1, totally correct. Plus W2 is again a constant, plus constant plus constant. Makes no sense, right? It's there. And if you want dE by dW2, then what will happen? It will give you X2, right? X2 into 1. Don't worry again to, okay, it's in chat. Just a second. Again, see, someone is asking me this question, that that is this really required? No, this is not required. This is just for your reference. Don't worry.
Shivam, I think
Okay.
you need to add a constant term too into the derivative.
Oh yes, yes, yes. So we need we add a constant term, but here we know that that constant term is equal to 0. So yes, he's right. We'll have some C1, C2, but these are constant as of now for us. They don't bring much value to us. I'll put this picture around. So see, this was just for one, right? If you go from here till here, this was just for adjusting the new values. Now what will be the adjusting values of W1 and W2? So now we already have the older values of W1, W2. So the new value of W1, W2 will be dW is equal to W1 minus dE by dW1, and W2 will be equal to W2 minus dE by dW2, right? This will be equal to this, and but there is a special term that is called alpha that is associated here. It is multiplied here. I'll tell you what alpha is here. I don't know how to type alpha in like latex, but okay. Okay. So now you might ask that, okay, now we understand that this is the new value of W1 and W2, right? So now what will happen? This older value of W1 and W2 will be replaced by the new one, and then you again go forward, and then you again get the error, again come back, change the value, again go forward, backward, forward, backward. But there is one thing that you might ask me, that what is this A here? This A is called alpha. Sorry, this is not A, this is actually alpha. and this is also called as learning rate, or you might see people calling as LR. Right, now what learning rate is, now just pay a little attention towards here, right? So let's say the previous value of W1 and W2 will give you some error that would be here at this point, the one that I draw very small here, right? The next one will be here, then here, then here. So it might vary that how gradually you are moving your W. Let's say that you are making very small change in W, very small change in W. So your error, let's okay. Let me maximize it. Okay. So now let's say you have taken some initial value of W such that W1 such that the error is here, right, at this point, at this particular point. Now you make a very small change in your W1 and make it to W1 dash. So what will happen? The error will shift very slowly also, right? Your error is also going to shift very, very slowly because you have made a very small change in W1. Or otherwise, let's assume that you might there your W1 originally was here and you made a very big change in W. So your error might be here at this point, new error might be here, or it might also happen that it might come here also, right? It might change that how gradually you're moving your W. So there is this terminology that says that you should very slowly move your W so that you don't miss your minima. Assume Again, let's assume that you slowly moved your hair till here. So you have come till here. Your W1 is here now. And now you suddenly increase, you did a change in W1 so large that you came here. You came at this point. Now this is bad because you missed the global minima in here, right? So what people say that you should very slowly move the value of W, very slowly. You should do all the changes very slowly, and your dE by dW, your dE by dW should be controlled by some another external factor, and that factor is called alpha. Now, because if you go down the screen, if you see, I have multiplied this dE by dW term with a thing called alpha. Now this alpha is with you. This is a constant and this is in your hands. You can change it anytime that you want, right? So what you will do is, I'll move back up here. So what you will do is that you will select the value of alpha such that it is moving very slowly, right? But now there's a disadvantage also, because if you move very slowly, then let's say you are here, then you will come here at this point, then here, then here, then here. So you might reach your global minima at a very larger time. It will take a lot of time to you. So you have to take a very critical value of alpha such that it moves very slowly. I mean, not
So,
slowly, but yeah.
are you trying to like tune up your model?
This is not tuning, it is just adjusting the thing, that how the model is reacting to the changes that we are doing. So it's like we are controlling our own process of the flow of gradients. And alpha, keeping the value of alpha, yes, you can say this is one of the parameters of hyperparameter tuning. Hyperparameter tuning, HPT. Yes, this is one of the small features that you are tuning. So the value of alpha you should keep is 0.001. But again, if someone says you this, well, like I just said you that you should keep your alpha, no, I'm totally wrong. It depends on your data, that how slowly you see that your model is moving. This is just the initial value that you should take. So if you will see all of your major frameworks like Keras or like Tensorflow, you will see that they have put a value of 0.001 also by default. Make sense? Till here, anyone is having any doubt? Let's say that if you want to do it for multiple cells, this is how it looks then. I don't want to scare you, but this is how this mathematics goes backwards, and then you do all the changes slowly, slowly, slowly. If you want to see the weights adjusted also, I have a picture for that also. Let me. Yes, this is how it looks like. Anyone, any doubts till now? Okay, I have some questions. Cool. No questions? Then I think we should move forward and I should show you some things. Okay, now I will take questions from the previous class that someone asked me that how does the image looks like, and I showed you this GIF, right? So I told you that this image is nothing but images are just numbers. Numbers ranging from 0 till 255, where 255 being the highest value and 0 being the lowest value, and these are called pixel values. These are pixel values, pi values, right? These are pixel values to you. These are pixel values. This is how the images work. But the image that you're seeing on your screen, this is a single channel image, right? This is a single channel image. Now you might have multi-channel image also. Let me show you the demo. Okay. Okay. Last time, anyone in doubts in backpropagation, because this ends your theory for uh, deep for neural networks, right? Neural network intro is done here, right? So MNIST was the data set where everything was written, in 1, 2, 3, 4 was written on images, and we need to predict out what is written on the image, right? I told you there are two things now. One is the image, and second is what is actually written on it. That is called labels, right? So we got the data set, and then we started doing it on Keras. But today we will do it on TensorFlow also. Why on TensorFlow? Because I want to give you a basic idea how code in TensorFlow is also written, and how Keras is helping you in how much lowering the works. Otherwise, you won't get to know that how much things Keras is doing in on itself, right? I'll do the first basic. And if you think this is not visible to you, I can switch to this also. NumPy as np and import. What else can we do? Matplotlib. And guys, I'm requesting you, please. I know many of you are working and you don't get time to do all these things, but please take out time and start doing at least some revision. Okay, I'll do these 3 imports. I'll check the version of TensorFlow that we are using. So I'm currently using 1.8.0. If you're using anything else, don't worry. R's code might at some place differ, right? Don't worry. But if your code varies, right? So how do I get the data? I get the data from TensorFlow.examples. tutorials.MNIST. So actually TensorFlow is already downloaded, not downloaded, but they have put this inside their in their syntax. So if you go inside these tutorials, you will get a lot of, I'll show you also. Let me show you how many examples do we have. I have also never seen these, but okay, so currently they have only MNIST here. They're adding slowly other things also. Okay, so we have MNIST here, then we do the input data also. Input data, let's say we do this. Anybody remembers the syntax that is called a read datasets? Read datasets expects from you is that it requests you the input data dot reads is first is the train dir. Where do you want to keep the data, right? You can see all these things written here, right? Train data, fake data is equal to false. Yes, we don't want to fake data. Hot. Everybody remembers one hot encoding, right? That we did last time also. If you have any doubts, please ask. Let me know. The current default D type of the data is float 32. That's good for us. Reshape equal to true. Validation is equal to 5000. That's correct. Seed is equal to none, and source URL it is written here. So the URL is actually here from where it is going to download. So you don't have to tell it the download for it, right? We will just say where do we want to keep the data. So I'll keep the data in. I'll keep the data in MNIST underscore data, right? This will create a folder there, MNIST underscore data, and I want the one hot encoding to be on. So sorry guys, I don't have space to write because of this true, right? Okay, so what has happened here is that now by default, if I see and go in my data section here, so I might have a MNIST dataset in my data folder, right? I'll show you. I have the data folder and see here is this MNIST data, and all the four files are here. Which four files? If you remember, we did this also. MNIST, right? These four files that we saw. Yes, that also. If I'm not wrong, we have done this I have shown you this website. I've shown you what data set it is, right? Correct me if I'm wrong. Okay, so now what we have done is we have downloaded the data and it is in the one hot encoded data sets, right? Now I did one mistake here. I should have first of all said import warnings, and warnings dot filter warnings and ignore. Why I am doing this? Because I don't want to see this all warnings here. You can see this is just warning. So I don't want the warning to be displayed every time. Just don't want it. So now you will see no warnings. Correct. Now let's see what is inside MNIST. If we check the type of this, so it says it's a dataset type of a thing. Let's see what things it can help us. Okay, so it has actually three things: test, train, and validation. Let's go inside what is this test train, and you can see that there is dot index and dot count. It means it's actually a tuple. It's actually inherited from a tuple thing, right? Let's go inside train. Train may, if we see, there are images and labels, right? Let's go to images and then let's see what is the first image. First is this image. This image looks like something like this. Let's do one thing. Let's print this. Let's plot this image, right? How do you plot this image? plt.im show, right? But im show will take two things. What? At first you need to make sure that your image is a 2-channel or 3-channel image. But if you see what is the shape of your current image, currently it is 784. 784 is not a valid image, right? Our image should have a width and a length, height and width simultaneously, right? So there is no. So what you have to do is that you have to do a reshape of this also. We know 784 is a square of 28 cross 28, and we know these are the images of 28 cross 28. Now you get 28 cross 28. We'll do a 1 also. Why? Because I want to show that this is a 1-channel image. Now if I do a plot, sorry, my mistake, right? What we can do more is that we can make it gray so that you can see the actual color. This is how it looks like, right? So the first image looks like this. This first image looks like this. What I can do is I can print the label also for this corresponding image. I'll say print MNIST dot train dot label, but I have to make sure that I'm giving it the same number. So if I've given 0, then I'll give 0. Because this is 1-hot encoded, now the data is in 1-hot encodation, and you can see 0, 1, 2, 3, 4, 5, 6, 7, right? So you can just say control Z. I can make a function out of it, and I can say plot underscore image, and we can accept a number from the let's say we want to print 59900th image. This is actually a 0, 1, 2, 3, 4, 5, right? I'll take a pause here. If you have any questions, queries, please ask.
The above definition, what can you please explain what that is MNIST train dot labels number?
I am sorry. Can you ask again? I'm so sorry.
In the above definition, define plot dot. So in that, what the function
Okay.
does.
So what MNIST is giving you? MNIST is giving you 3 types of data. If you see here, if you pay a small attention, it says 3 things: test, train, and validation, right? So now what you did was you went into train and then you said how many things are there? There are actually 2 things. There is images and there is labels also. So labels and images, imagine there are a very long list, a long array, where for every corresponding image there is a number written there. So what I'm doing is that I'm asking MNIST that inside your train data set, if we have images, give me a image called num. Num is actually a function here, right? So num is actually containing 599. So what is the 599th image? Just try to plot it. Now because if you see the shape of MNIST train images, it is actually 784, 0. Now a image is not actually a 784, 0, right? It is flattened image just to save the data, right? So what we're going to do is that we did a reshape of this image. Because we already know from the Yanlikun site, if we go to the Yanlikun site, you can see here that they have clearly written that the image is actually a 28 cross 28 image. here if you see. If you read this very carefully, it says 28 cross 28, right? So we know that how that number 784 came from. So what we are doing is that we are now converting it into dot reshape 28 cross 28, and then I'm asking, don't print the normal image, just print me the image with the grayscale tag. Any issues? Concerns? Then the number I gave it for image, I'm giving the same number for the label also. Make sense?
Thank you.
Okay. Any other person who has any doubts, concerns? If not, we'll rush further. Right, once we have got all the data, once we have got everything inside us, what we are going to do is now we are going to make TensorFlow variables. So to store all these images, weights and biases, we are going to make placeholders, variables and constants. If you remember these definitions, so what we are going to do, we are first going to make a tf.placeholder. This placeholder will keep all the images, and we'll also have a y that will be that will a y that will contain all the labels, right? For every image there is a label. So what will the model do? Model will try to learn all the features from the image and try to map it to 1 2 3 4 5 6 7 8 9, right? So what we are going to do, we are going to say tf.placeholder. So first is actually the d type is df.float 32, correct? Then it asks for the second thing is that is shape is equal to none. No, we don't give shape is equal to 28 cross 28. We give it the full image. We are not going to do the unfolding of the image. We'll let it remain flattened only, right? Now we are going to make the weights. How do we make the weights? Weights is equal to tf dot variable, right? By default we are going to initialize them with zeros, correct? How many zeros? 784, the number of inputs, and the next column output will be 100 only, right? Can anybody explain me how did I came with this number of weight 784 into 100? Anybody? No, I'll tell you. So see, what is happening here is that we are creating a variable called w. Now what this w is going to, correct. So our neural network will look somewhat like this. But sorry, we don't have so many. So let's say this is the input. But we have only 10 outputs. This is the input layer. Input layer has 784 columns that we already know. And I think who answered that correctly? Okay, and this is the output. This is the output, right? So what is happening here is that you have 784 inputs of an image inside your input layer, and then you have 10 outputs. Now how many weights will be there inside? Let's say that this has to connect to every 10 of the outputs. 3, then 4, then 5, then 6, then 7, then 8, then 9, and then 10. So this is just one input. Then you have 783 other also. So what will be the number? Right?
So
Everybody understands this?
7,840 probability.
That will be 784 into 10. Right? That means number of weights we will have inside our thing. Right? And I did a mistake. Sorry. I should have written it 10. I have written it 100. Sorry. Right? These are number of the weights. And can anybody tell me how many biases will be there? Anybody? How many weights? How many? Sorry. Biases, correct, 10 only. Why 10? See, because you will connect this 784, let's say these are 784 and these are just 10, right? 1, 2, 3. Where are the biases connected? On the this end. Okay. Now once you're done with this, W,
Sorry, Shyam, to interrupt. You said that biases will be connected means this 10 biases into the number of hidden neural
correct,
neurons, right?
correct. I'll explain you again if this is not okay. Other people also wanted to. I'll tell you. So see, again I'll draw. Let me bring out my. It's not here. I lost it. Okay. So see, what is this? This is your inputs, right? These are your inputs. And let me change my pen. This is your output. Now, how many outputs do you have? Only 10, right? Currently, I am drawing just 5. Now, how are these connected? These are connected somewhat like this. So, weights are connected to every node, right? Everything is connected to everything, right? So, you can, what you can do is how many weights will be there? Input into number of output, right? Input into number of output is equal to the number of weights. But how is a bias connected? A bias is connected somewhat like this. Let me give you an example here. A bias is connected to every output neuron like this. B1, then B2, then B3, B4. Or you just imagine that bias is nothing but bias is actually a input only, but that input value is 1. So let's imagine this is x0 here. And you have input called from x1 till x784, right? These are inputs. Now just imagine one thing, only one thing, that if you have outputs here and these outputs want to connect to this x0, how many lines will you have? If you want to connect this x0 to every output, how many lines will you have?
It will be number of output
Right?
into, yeah.
Number of outputs only, because you're connecting just x0 to outputs, right? So now how many outputs will be there? That will be number of biases, right? So how many outputs do we have?
10.
10. So the bias will be 10.
If we consider only one means direct, in this case we are considering one net only, right? One input
Correct.
layer and output layer.
Correct. So what we are currently doing is we are just making it for one layer, right? So if you are making it for multi-layer, then you have to do it for every layer, from here till here, then for here. So you have to do it for every layer.
Yeah.
Did I make sense?
Yes.
To Omar also? Omar, is this helps you? Concepts of biases? How did biases came up? So bias, imagine bias is nothing but actually an input called x naught whose value is just 1. Cool? Little bit? Still query, please ask. Whatever you have in your mind, just let me know. I have to read a little bit more. Okay. I think I suggested you guys a book called Neural Networks and Deep Learning by Michael Nielsen. That is a very, very genuine book. Please read that book. That is very helpful. I was reading that bias is threshold value. Threshold value of what? I did not get it. Okay. You are saying that I did not get the book. Okay. I don't understand. You didn't get the book URL or the content, because book is free. I'm again posting the URL here. No, I think I posted the URL here only in the chat only in the last class. This is the book. Do read it. It's pure theory. The people who want to go inside the theory of neural networks and deep learning, they should definitely read this book. There is no escape from this book. Please do read this book. Okay.
Yeah, Shivam.
So what? Yeah. Sorry.
Yeah, actually, the bias is for simplifying the mathematical calculations, right? Am I right?
Correct. Totally correct. So what happens is, if you're going to be in the let's say in a binary classification problem where there's only one thing, that is true or false. At that time we face this issue when we are calculating the cost function. That time we face this issue. That's why we have to introduce this thing called. So just think of bias as a weight only. Just think of.
Here, like in the same book which you mentioned, I was reading that neurons output 0 or 1 is determined by the weighted sum, which is less than or greater than the threshold value, and that threshold value they call it as bias.
Correct. So why they have written this is because, let's say that your bias, that your weightage is going nothing. It's going nowhere, right? Let's say it's a 0. Then who is going to decide your output? So a bias is actually a safe side prediction, where not a prediction but a safe side calculation that we do to avoid things. So whenever you will do a binary classification, you have only one thing, right? Either true or false, right?
Yeah,
At that
0 or
time,
1.
when you will calculate a cost function, you will get an error there. That how will you produce for 0 and how will you produce for 1? That's why we need to introduce this thing called bias instead. So just consider bias as another weight where it is actually connected to a input, where input ka value is equal to 1.
Weight or weighted summation of
No.
input
Weighted.
and weight.
Only weight. No, I'm saying just consider, just for simplifying the process, just consider bias as a weight only. And weight of what? Weight of an input called x naught, whose value is equal to 1. So when you what is actually that we are doing is that we are multiplying every, what are we doing in the affine? Affine mein we are multiplying every input with its weight, right? You remember the affine equation, x1 into w1 that we discussed in last class. So if the value of, we do like this, right? x1 w1. So what is happening is the value of x1 is equal to what? I'm saying keep it 1. And that becomes a p.
So whatever you're calling that, is this called this perceptron model? Because I was reading perceptron, yeah.
So perceptron model is nothing, but it is the same model that I showed you on the very first day. That was just single neuron. and a
Yes.
affine was happening. Remember, I was just showing you a
Hmm.
single neuron where there is only one circle, and an affine is going on and an activation is going on.
Hmm.
That is what
Correct.
represents a single neuron entity of a neural network. Now let's say that we have declared these three things, X, W, and B. These are the three things that we want to declare. We also want to make a Y also, correct? See, how I am going to declare Y is very important. I will say tf.nn dot softmax. What is softmax? You guys remember? Softmax was an activation function. What was that doing? Can anybody tell me? Okay, how many are able to relate to this thing that I have written?
Shivam,
Matrix multiplication.
Okay, and how? Okay, so you are totally correct. And how many of you can relate this thing to? Just a second. Where is our last class? Just give me a second. Last class. Theory to intro to neural network. And how many of you can relate to this thing? How many of you can relate this with this thing? This sentence that I've written here on the top, and this one. You decide. Then till then I have functions. Yes, Khem is totally right. It is called a affine function. And then Sanket is asking, deciding which neuron to turn off and turn on. So sorry.
I was saying that softmax function decides which neuron to be turned off or turned on the basis of weight and biases.
Uh, Exactly not exactly, but you are somewhat right, but that is a special case that you're talking, just a special case where you're talking, and that is called a binary classification, where that's just true and false, right? So it has no option. So what it will do, it will go with the maximum probability, and it will say, okay, because the weights are more, you are allowed to go, right? Whereas what is a softmax function? Can anybody tell me the equation of a softmax function? Summation of e to the power minus z above e to the power minus z. So what this actually is doing is, it is taking all the probabilities of all the things, and then it is making sure that the probabilities ka sum is equal to what? 1. So let's say that we are doing a MNIST problem, right? Where what are the different outputs that we can have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we can have 10 outputs, right? So what will the affine do? Affine for every output. If I show you, just give me a second. So whenever your output is there, just imagine these are the 10 outputs, right? And you gave a image of 5, right? What you did, we gave a image of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are 10 outputs, right? And let's say this is the fifth one. Sorry, let's say you gave the fourth image, right? You gave the image called 4, right? You gave this image that was looking like this. Now what is happening? Now the neural network has done all the calculations, and it thinks it's the fourth image, right? So what it will do, it will give probability. It will give probability for every class. It might be high or low, but the model will, at every output, model will give some probability, that this is this probability. I think probability of having a 1 is this, probability of having a 2 is this, 3 is this, 4 is like 98%, right? And it will give probability for all. Now what you will do, you'll pick the maximum one. Now who is giving these probabilities? Actually, softmax. Softmax is distributing. So Oman is saying that so it is just converting data into probability distribution. Yes, totally correct. Totally correct. It is converting the data into data probability prediction. So softmax is converting all the numbers into probability distribution, whereas the sum of all these probabilities, all the probabilities that it is giving you out for all the outputs, the sum of all this should be equal to 100 or 1. I mean, if you're taking in terms of percentage, it should be 100, and if you're taking in terms of probability, it should be 1. Make sense, Sanjay? Omar, making sense to you also, right? Helping out? Cool, 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 cool. So, yes, I was asking one thing, that is this photo saying the same thing that I've written in this highlighted cell also? Yes. So we have converted this operation that is showing in this image into this one line, right? Softmax का code, I mean, you can see the function. The function is if you see the softmax का function, it's e to the power minus z upon summation of e to the power minus z. If you want, I can send you all the sheets with all these formulas and all. Right. So we asked, first we did the affine, we did a matrix multiplication of x and w, then we added bias into it, and then we did a softmax of the whole thing. Right. We have done this thing, right? This is the one that we are going to calculate. This is the y that is being calculated, but we already have the y that is with us also, right? That is called y actual. We also have the y actual with us. So we have to create that y actual also, that is called dot placeholder. We'll create a placeholder for that. Placeholder should be of 432, and the shape should be, can anybody tell me? What will be the shape? That will be 10 only, right? Why it will be 10? Because our image will have only one thing, right? If this is the image, the output will be 4, right? Why I am giving 10 here? Because we did a one hot encoding, you remember? On the above, we did this one hot encoding here at this point. Now what does one hot encoding does? One hot encoding says that your data is actually not in the form of 1, 2, 3, 4. Now it has converted into zeros and ones, and you can see it here very much correctly at this instance. Whenever you are writing 5, you are writing in this format. Correct. KM is totally correct. It's 2 dimension. So now what is going to happen, that for every image, the answer will be in 10 length, right? That's why I'm giving this. Right? Makes sense to everyone? Now what I'm going to do, I'm going to do the cross entropy. What is this cross entropy? I'm telling the neural network that you have to go back and do all these things also. So what I'm doing, I'm saying him to do a reduce mean. I'll tell you what I'm doing, don't worry. Reduce mean of tf dot reduce sum of what? Y minus ya minus tf dot log of y. I've done the sum here, and then reduce mean of this, comma reduction indices is equal to -1. Not -1, it should be 1. I know this is a bit tricky, but can any one of you want to try this thing? What is actually happening here? Okay, I'll tell you what is happening here is at this particular step, what we are trying to do, we are trying to calculate the errors for back propagation. What we are going to go, we are trying to calculate the errors. And you remember error was actually what? In the last class we discussed this also. What was error? Error was nothing but y actual minus y predicted, right? This is what I have written here also. This is y actual minus log of y predicted, right? Now what I'm doing, because y actual and y predicted will be, let's say this is the output for all the cells. So it will have some y actual. Let's say it is the image of 4, right? So 4 image pe y actual will be 1 here, right? And other than that it will be 0, 0, 0, 0, 1, and then 0, 0, 0. And let's say it's giving some probability 0 0.01, 0 0.02, 0 0.1, let's say, and at here it will give 98. So what you have to do, you have to minus all these things, right? And then add up. I'm doing the same. I did a minus ya minus log of tf log y, and then I did a sum of it, right? Reduce sum of it, and I've reduced it to the indexes first index, right? And then I took out the mean of it, because it is the cross entropy is the mean actually. You divide by the number of observations. That is called the cross entropy. So you have the cross entropy with you now. Everybody gets the idea? I'll take a pause here. Have a look at the screen.
This reduction indices one, this I couldn't understand.
Okay, so see what is actually happening is that these why we wanted to go with the numpy also, but okay. So imagine you understand these are outputs, right? These are output neurons, right? And let's say the image is of number 4, right? So one hot encoding will say this is y actual. What it will say y actual? It will say ya upon 0, 0, 0, and it will here say y1 z1, right? And then 0, 0, 0 for all. And what will your y predicted say? Y predictive will give values for everything, right? It will give something. Let's say it gives 0 here, then 0.1 here, 0.1 here, then 0.2 here, right? And then let's say it gives here 0.9. Let's say it gives 0.9 here, so it will be 0.02. Let's say it gives here 0.9 and something. So what you have to do is you have to minus these things first. This is what we did also, right? We did a minus here, and then we got the answer. Let's say answer is here, and then we get the sum of this. But this is only for one image, right? We want to do it for all the images. So what is happening? I'm saying it to the model, that model do it on the first index. Now if you see properly, what is the first index in every shape? None here. And what is this none? This none is the number of images that are going to come inside this. See here, none. Now it's making sense to you? I can tell you again. See, what I'm doing is that I did this sum. You understand the sum?
Yeah, this is fine, yes.
Yes, you did the sum here, right? But we want the sum to happen over this axis called 1, axis 1. Now, what is on the axis 1?
The axis one, okay.
Right? What is axis 1 actually? This is called none right now here. If you
None
see
right
on the
now,
axis
okay.
y, none. And none is what? None is actually the number of images that we are going to supply here. So we want the sum to go across all the images.
Okay.
And then we'll take a mean of it.
Okay.
Is it okay to everyone? Okay. If it is okay. Now what we have to do is that we have to minimize this thing only, right? Cross entropy is actually our error, and we have to actually we have to minimize this. Now, how will we minimize this? This is called a training step. Anybody remembers the name of the equation that is used for backpropagation? Anybody? Gradient descent. Remember? So what we're going to ask to gradient descent, we'll say gradient descent, bro. We have this thing called cross entropy. Please reduce this uh, so please reduce this cross entropy for us. Minimize what? Cross entropy for us. Correct? Okay to all? Now whatever word we are going to do, what happens in TensorFlow? What is the golden rule of TensorFlow? It says that whenever you want to run something, you have to run it inside a session, bro. Ses is equal to, today we are going to use a new kind of a session. Let's say it's interactive session, right? It's actually a session only, but you can handle it very carefully, right? So it's actually made for what you call, for all your Jupyter notebooks only. So you can do a interactive session rather than doing tf.session. You can do interactive session, right? Now what you're going to do first thing when you, sorry.
Yeah, what is the difference between the session and the interactive session?
See, I'll tell you, tf.session is when you are not closing it, right? You have to explicitly close it. But interactive session will make sure that once the process is done, it will close it itself. And interactive session should be used only in Jupyter notebooks only.
Okay.
It is meant for that only, right?
Okay.
Once you make the session, what is the first thing that you always do? You will always remember global variable initialization. There are three things: placeholders, variables, and constant. You can run placeholders and constant directly inside a session, but if you want to run any variable inside your session, then what you have to do, you have to initialize them first. Remember? I'll do the same. I'll run it. Now all your variables are declared inside the session and they are ready, right? Now, but this doesn't do. What I'm going to do, I'm going to start a batch of I'm going to start a range of 500, let's say. At first, let me make it 50 only. So I will run a 50 steps, 50 forward and 50 backward steps for our training, right? And I will say batch. So what I'm doing, I'm asking the data to be given in batches. And how will I get this? I will say MNIST dot train dot next batch. It will automatically give me batches inside it, right? Then I have to increase this also, because how many training samples do we have? Let me check, just 1 second. MNIST dot train dot images dot shape, we have 55,000, right? So I have to make it 550. Did you get the calculation what I'm doing actually here? So what I'm asking MNIST is that MNIST, please don't give me all the images at once. Give me 100 images, and that I will take it in every step, right? And if I am going to take 100 images, then how many times do I have to run the loop? 550 times, because I have 55,000 images, right? Making sense to everyone, right? Because we have 55,000 images and I'm taking only 100 images at a time. So I have to take 550 times I have to run this thing to complete all the images, right? So what is happening now? It will give me batch X and batch Y. Batch X will contain all the images and batch Y will contain the correspondingly labels of the thing, right? I'll do nothing. I'll just say ses.run and I will run the train step, nothing. And I will do a feed dict. Now I have to feed the dictionary also, right? Because I have taken two placeholders. One is this YA and another one is this x, right? So I have to feed these x and y also. I know the x is nothing but x is what? Batch x. batch x. And I know my y underscore actual is what? Batch sorry, batch y, right? Now if I run this, it will run the session for me. Enter. So now what is happening is the session is going to ask what is train step. So train step will say that you have to do a gradient descent optimization minimization for cross entropy. It is going to ask who is cross entropy. Cross entropy will say that I'm a reduced mean of a reduced sum of ya and y. So it will go back and it will ask, okay, ya, you are a placeholder, I get it, but who is y actually? So he'll say, okay, y is actually a calculation of x, w, and b. It will ask what is x. X is again a placeholder. You get the value from your feed dict. But who are w and b? It will say w and b are here. Everybody gets the idea how a session things work in TensorFlow. Please ask your questions right now, otherwise it will become a little messy afterwards. And again, to all who are not getting this also, don't worry. Kiras is much. Yeah, sorry.
Yeah, hello, Shivam, Sanket here.
Yep.
Actually, I want to know means how we decide the batches. Means taking in a huge number means in some image processing examples, we have to reduce the size of the image, and after that we have to train the means neural net, right? So
Correct.
the size of the image and the number of batches we train, it
Correct.
affects the means what we can say time of that means
Correct.
processing
Correct.
speed also. So how
Correct.
we
Correct.
decide this range means this batch?
Very good question. Very good question. Now I'll tell you answers slowly one by one, right? So first of all, why do we take batches? Okay. The concept of batches came because we don't have as much as RAM we can afford, right? Because we have a limited RAM resource, right? Let's say we have 1 million images. Now, can you just put 1 million images in the forward and neural network? No, never. You have to give them like 1,000, 10,000 images one at a time, right? Because our RAMs are limited, right? We still don't have processing power that can take all the images. Now your question comes, how do we decide this batch number, right? Let's say that we take a very large batch number, right? So what is happening that all the images are going try to go inside the network, but again what will happen that because all the images are going together, it will go fast. Definitely it will go fast, but again the RAM will exhaust at one limit, right? Let's say that we reduce the image only to one image at a time. Now give me now I'll ask you this one simple question. Okay, you decide and tell me. So let's say that I ask you to classify let's say two animals, and you have never seen those animals, right? These are some African animals that you have never seen, right? And I am showing you only one image, and I say let's say the animals name are animal A and animal B, right? And let's say I only give you one image at a time, right? And then I say you that Sanket, this is animal A. Now give and the next time I show you the image, I ask you that what is the probability of animal B. You will say to me that bro, I have never seen animal B, right?
Yes.
Right? You will say this to me, right? That's why we cannot minimize the number of batches also. So we have to make a certain ratio of the batch number such that the model is also getting generalizedly trained. Are you getting my point? What I'm trying to say? This is pure theory. That if you're giving a very less number of batches, then it's difficult for the model to run. But if you are giving a very large number, then you're forcing the model to learn multiple features in just one go, right? That's why you have to decide this number very precisely based on how many features in your images do you have, how difficult your images to categorize, or let's say that if you're training on two images, that what is the difference? Is the difference very significant? So it can be caught very easily, or is it very difficult to catch? Right? That's how you define this batch number.
Sorry, one more means I just wanted here is means we have to choose precisely, but how can one choose means if he knows the parameters, means if he knows the number of images and the number of features which on which he is means differentiating the image, right? How can one decide on means considering these parameters? Uh,
I
how can
totally
one decide
understand. Correct, correct,
means
correct. I
you say
totally understand
precisely.
your question. I
Actually,
had the same.
uh,
Please
yeah,
go on.
I have ran some image means image what I can say
Classification
classification problems,
models.
but at the time, yeah, I was not
You
sure
have no idea.
how
Yeah. What
yeah.
batch
So I
number you
was
should take.
trial and error. I was doing trial and error, which batch, how much batch, and the resizing of the image was also a little bit tricky one.
Mm-hmm.
So
So okay,
I
yeah,
mean,
I have to answer one more of your question, that how do you do uh so Khem is writing correct, yet more data, more model, more effective. Yes, that is true. That is certainly true. But okay, Sanket, to your answer is, first of all, let's say that you're talking about this thing again and again, that what is this resizing thing. So see, why majorly do we resizing is because, see, if you're giving a HD image to a model, it doesn't make sense to it, right?
yeah, actually,
Right.
I'm not saying about resizing. Resizing also is also one of the factor because
Uh,
if I resize the image to a very small size, means suppose a 1000 by 1000 pixel image, if I reduce it by to 20 by 20 pixel image, then the processing speed for that entire data will be fast enough, right? But it will minimize the features in that. So if I reduce to that to some 500 pixel to 500 pixel, then the it will take some more processing time. But when I take 20 by 20 image size, then I can give a large number of what I can say batch size. But if
batch
I
size. Correct, correct, correct.
yeah,
I get the idea.
but
What you are trying to say. So just to RAM to accommodate. So this is a very good mathematical calculation that you are doing. That if you reduce the resize the image to a smaller content, then you can give a very large batch number. But you have a very high definition image, then you have to make sure that your batch size is very limited. But you have to make sure, Sanket, here, that you have to see that you should not even reduce your image to a very small extent that even model cannot take out. So because if you go and see the algorithm, that how does the cv2 dot resize work, or how does the image resizing algorithm work, the features are somewhat lost. But you have to now make sure that at which extent do you want to resize your image, right? Second
yeah,
is,
absolutely true.
so see, why I'm saying this is because, see, at the end of the day, when you are resizing your image, so the next time when you're doing the prediction from this model also, that time also you have to reduce this image size.
Yes.
So I'll say it again. So if, let's say that you reduce the 1000 cross 1000 image into 200 cross 200 image, and then you made your
Hmm.
model. Now what you have to do is, then while you are predicting the images, at that time also you have to make sure that your images are reduced to 200, and then only you can do the prediction also.
Yes. So, is there any some mathematical formula or means some kind of calculation? So, can one decide to means approximate batch size or like that?
So okay, yeah, correct, correct, correct. So see, I'll tell you. First is that it totally depends on the data that you are working. So I'll tell you two different use cases. I'll tell you two different use cases. One is that you're working on this thing called on a classification of nut and bolts. So nut are circular. So nuts are cylindrical in size, and bolts are hexagonal in shape, right? This is one thing that you are doing. And second is that you are working on the very minute wiring section, wiring classification. So you have a model of
Mhm.
multiple wires going inside. So have you seen that image, that when multiple LAN wires are going inside server farms, right? That image
Yeah,
is given to you,
you can
right?
say of PCB,
Correct, correct,
a
correct. Or
PCB.
PCB
Yeah.
also. Correct, 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 correct. PCB motherboard connection you can also take, right? So now you're
Yeah.
working on this minute thing, right? So now
Mhm.
you have to make sure that how is the model going to differentiate, right? So it depends on the data, right? So if bolt and nuts are there, they're quite differentiable at the very first instance, right? And if you're working on wires, they're very minute, and it's even difficult for humans to differentiate. And how can the model differentiate, right? So first is the first thing is data. That your data is the first thing on which you can decide this number. Second is that people have made generic models like VGGNet, ResNet, and ImageNet. So what I generally do is that I take inspiration from these papers, from these models, right? So because you see, we don't have much time to experiment with this because our client is standing there, right? Second, this is the second thing, right? So what I do is I take inspiration from other models, right? Third is that I do this elbow thing, elbow algorithm. What does elbow algorithm says? It says that it is a generic equation for every brute force thing. So what you do is you draw a graph here. On the y-axis you have the error of your model, right? And on the x-axis you have the batch size. So what you do, you start your batch size with, let's say, 1, and you go with 10, 20, I mean 50, first 10, and then 50, 100, 200, and then you go with the maximum amount also, right? Then you
Yeah.
will see a graph somewhat like this at this section. It is almost like a elbow, our hand elbow, somewhat like that. And this is your optimized batch size that you should take. This is the optimized batch size that you should always take. So first thing is your data. Your data will tell you that how much you have to resize it. So I'll tell you how do I decide this. That I told you that I take inspiration from other models. So I have seen that VGG works on the 2 to 4 dimension. So they resize the image to 2 to cross 2 to 4 cross 2 to 4. So what you can do is that you can resize your image to 2 to 4. And I have seen bigger models like the new model that I was working yesterday. It took an image of 500. So I have never seen a model with more than 500 cross 500 image. But again,
Okay.
it depends on your data. Again, it depends on the data,
Yeah. Right.
right?
hmm
See, batch size is just one number, right? Now you have to decide multiple things. Like, first
Yeah.
is batch size, then how many layers, then in one layer how many neurons. So there are multiple hit and trial that you'll do. And believe me, I asked the same question almost 5 years ago to my mentor also this, and he was also giving me something that you will decide with this experience. And the more models you will make now, you'll get the more ideas.
Okay.
Slowly, whenever you will be dealing with data, you'll get the idea. Okay, this is quite difficult, difficult for the model to train. So I have to leave the model to a very specific area. So you'll reduce it to very specific area, and you'll crop it in a very good manner, right? And then you will give a generalized batch size, right? So right now what here we are doing is that we are giving it a random batch size, right? So model on itself is taking random images from itself, right, from the data pool. But sometimes, let's say that I'll tell you, I was working on this example of watermark detection. So what I was doing, I had to build a classifier model whether there is a watermark present or not. Okay, so now tell me, how will you do this problem? Any ideas?
Watermark means visible watermark, you are saying?
Yeah, so watermarks we see on the images, right? So there is this problem. So let's imagine that you are a real estate client, right? Let's say you are housing.com, right? And now people are uploading photos on magicbrick.com also, right? So what they're doing is that they're uploading images from magicbrick.com to your portal also, housing.com also. And this is a
Okay.
violation of rules, right? Because magicbrick.com has its own priority images, right? They have their watermark on those images. But now people, what agents are doing to save time, they are uploading the same magicbrick images to your portal also. And now magicbrick will sue you. Why? Because you are using his images, their
hmm
watermarked images. So you have to restrain the users from using those images. How will do it?
First, I have to identify is there any watermark of
Correct.
magic
So
brick
you have to build
on
a
that.
so you have to build a classifier for this only. That you have to tell that this does this image contain a watermark, yes or no.
Right.
So see, this is a very I worked on this problem almost 2 years back. So what was this problem? This had the same problem. So imagine this is a image, right? And similar to this image, same copy of this image but with a watermark at a very small level. Now watermarks, you know that watermark are not colored in nature. They are transparent
Yeah.
in nature, right? And they work on the alpha channel. So what is this? That
Correct.
they don't even have some color on them also. So what you can do, you cannot even convert your image into a single channel image also, right? So you are asking this question, what is the resize? I'll give you one more problem. Other than resize, you have one more problem. Rather than converting your problem into a single channel image, you have to keep it now into 4 channel image, right? And if I reduce this image size, what was happening? The logo was the watermark was getting squeezed out, so I could not resize the image also. So that's why
Okay.
I had to take a model with the constant image also. So it depends on the problem on which we are working, right? Second, I'll tell you, I was working on this PCB wiring also. I was working here, and this was not actually a PC wiring, it was actually a car wiring system, right? So there was this engine was also in the photo, there was multiple things inside the photo, and there it has a very small slot in which images were going inside, right? Now if you give the model this whole engine and all these things, all those noise also, the model is not going to understand anything. So what I had to do, I had to crop this section first of all. This small section I had to crop this small section, and then I had to give it to model, and then only I could do it, right?
Yeah. Yeah.
So so your question is totally valid, and I can totally relate to it. I had the same questions. I did the same questions, and I also could not get this. But believe me, slowly. Yeah, interesting news. Yes, bro. So you'll get interesting problems in AI, and the best part about AI is that what is happening now. We are out of the bubble phase right now, so everybody understands. Okay, things work on their ways, right? But still people they have very interesting use cases, and they ask you that can you do this with the um, AI, can you solve this with AI, or can you solve with this section? And imagine, you'll believe me, you'll come out with some other way. You will come out some other way that you guess you can do this, you can do this and that and that and all, and you'll come with it. Don't worry at all. Yep. Sanket, I know I couldn't give you a correct answer, but did I make sense to you? Because see, you can
Yeah.
read multiple blogs. I mean, you'll read multiple blogs and multiple books. You will not get a correct answer anywhere. Even if someone is
Yeah.
giving you an answer, even if someone
I've
is giving you answer, he is giving you for a particular problem. He is giving that. Okay, let's say he's saying take you take the resize as 300 cross 300, but he is giving it for his particular problem, right? So that's why there is this
yeah.
thing. So that's why what I
Yeah.
do is, if you want to generalize something, go with these models like VGG. What is VGG?
We,
VGG is actually a model that is made by Oxford University on ImageNet.
yeah, I've gone through some blogs also
So
and
what I
some
take is, I generally
uh,
take help from these things, and then I work on it. And you should definitely follow this guy, Pi Image Search. He's a very good guy. And if you're especially interested in images, you should definitely um, this blog is your savior.
yeah, it's
So,
of Adrian
these are the models.
Rosbeck.
See,
Yeah.
VGG, yeah, Adrian Rosberg, yes. So VGG, ResNet, Inception. So you should definitely go with these things because they are trained to be very generic in nature. So they have almost 1,000 categories to classify, and they are trained on 1 million images. So you should definitely take inspiration from these things. I generally take the inspiration from these things because these are made by one of the greatest people in deep learning and AI section. And second part is that they are very generic in nature. So I take inspiration from them. Correct. Now, once what we have done here until this 33 step is that we have taken a batch of 100 images and we have trained the model. Now let's see that how do we get let's say ACC is equal to TF dot equals, what is TF dot argmax? Argmax what of what? So let's say YA comma 1 comma TF dot argmax of Y comma Y comma 1. So ACC will come out to be ACC will come out to be what? Where is the ACC correct predictions? ACC dot run. So why is this not eligible to us? Just a second, just a second. Okay, sorry, I have to cast it also. Sorry, my mistake. I should say this as TF dot reduce mean, TF dot reduce mean of TF dot cast, ACC with a correction of TF dot float 32. Correct. And take it into the ACC. This is not actually ACC, this is actually correct predictions. Sorry for this thing. We have to run sys dot run. If I run ACC, what things I have to give? I have to give a feed dict of what I have given, only YA, right? So y is equal to I have to give MNIST. Okay, I have to give X also, sorry. X is equal to MNIST dot test dot images, right? And y is equal to MNIST dot, why is it not working? Dot labels, right? And did I have removed the section? I have to put a question mark also. Okay. What is this? Says placeholder shape 10 GPU device placeholder 2 data type. This okay. Sorry, see what I did, I was giving test here and I give train here. I have to give test. Okay, again. Sorry for my mistake. So it comes out to be 0.098. Already running good. I mean, it's not good. The probability should be 0.098, but we didn't have done much of the thing. Only it is just one perceptron. It can give this accuracy right here, right? This is just to show you that how things will work here and how you can do what I was saying. How will you do multiple things out of it, right? What you can do, you can get your, I think, weights also. Simply you have to do sys.run and you have to get out your W here, right? WN, you can get your weights also here. So these are all the weights, and weights should be 784 into 10. These are your weights. You have your weights here. Similarly, you can have your biases also here. Biases you can have .sys.run. Now you can do B. B.n should be equal to 10 only. Yeah, 10 only. You can do C here also. Right? This is just to give you an intuition that how will you do a change. Sys dot close, very important. Just do this.
Right guys, just a quick info. If you're interested in doing an end-to-end certification course in artificial intelligence, then Intellipaat provides us the right course for you to master all of the concepts with respect to this field. And you can check out the course details in the description below. So this brings us to the end of the session. So I hope that you've comprehensively learnt about Tensorflow. And also do subscribe to our channel so that you don't miss out on our upcoming videos. Thank you and happy learning.